kinematic reactions or whatnot. Yeah. There is still a lot of very few people doing I think it's becoming more because it's becoming easier, right? Like, but I think it's like still like years deep in ground state, like because with all these foundational models and whatnot. Yeah, but you often need better types of theory, right? That you're already training on, and you have different observables you need to train on. Yeah, it's not as straightforward.
Okay, good morning everyone. I see not everyone managed to wake up today in time, but we'll start. So I'm glad I can introduce Johannes, that is going to show us about non-adiabatic dynamics. So.
Thank you. Yeah, good morning everyone, also from me. I'm honored to kick off fourth day of this meeting. And I want to talk today about machine learning for non-adiabatic dynamics with a special focus on architectures that you might want to need in order to learn more than a single electronic state. So, why non-adiabatic dynamics? Well, if you have anything that is related to photoexcitations, so in photochemistry or photophysics, depending on whether chemical bonds are broken or formed, electrons get excited, and therefore your nuclei experience a different potential energy surface because of some high electric state. But if the molecule would just remain up there, we could do everything the same as we did in the ground state. However, usually those higher lying electronic states, they interact, the molecule relaxes back to the ground state, and because the electron relaxes back to the ground state for different configurations, the Born-Oppenheimer approximation breaks down, because then we get a coupling of our electronic and nuclear degrees of freedom. And therefore we need special algorithms in order to describe our time evolution, and we also might need more quantities in order to describe these dynamics beyond simple energies and forces. And now just a little mathematical backdrop. I promise this is going to be short. So when we solve usually the time-independent Schrödinger equation, most quantum chemical programs solve the equation here for what is often called the molecular Coulomb Hamiltonian, which consists of the kinetic energy of the electrons, the interaction of the electrons with the electrons, electron-nuclear term, and the nuclear-nuclear term. And then the quantum chemical program solves the eigenequation, usually for the ground state, but maybe also for excited states, and gives you a set of wave function energies and forces. But what we're actually interested in is usually then this total Hamiltonian here, which has this MCH term, but also additional terms, for example, spin-orbit couplings, if we're interested in interactions of states of different multiplicity, for example. However, we get this kind of through the back door because we still only solve the I functions for this one. So now we need to propagate our system in time, right? Electrons and nuclei together. In order to do this, we want to have we need to solve the time-dependent Schrödinger equation. So where we have our electronic wave function on which we apply our total Hamiltonian, which might have these additional terms. And then we express our electronic wave function here as linear combination of our eigenstates of our MCH Hamiltonian. And then if we apply a bra from the eigenstates, we can derive an equation for how our these coefficients evolve in time, and then we can see they depend on here this matrix element from the total Hamiltonian, which because it has also extra states might not be diagonal anymore, and then we have here the time-dependent overlap of two different states. The thing is, when we have access to wave functions, like for example when we do machine learning, we cannot evaluate this overlap because we don't have a wave function. Then we can do a trick here, and we use the chain rule, and instead of doing the time derivative of this, we actually do the derivative with respect to the coordinates and then multiply with the coordinates derived over time, so the velocities. And this here is called the non-adiabatic coupling vector. So there are some approximations where we cannot propagate these coefficients in time. We do not use the non-adiabatic coupling vectors, but in principle we do need them. So now, how do these states actually look like? In principle, here MCH states look like this, which is probably the kind of the diagram we're most familiar with. And these states are called also adiabatic states. I will refer to them as adiabatic states, meaning our labels like ground state, first excited states, S2, T1 are just labeled in energy going from lower to the top. However, those states might interact and or even intersect, and if we then take our total Hamiltonian, not just the MCH Hamiltonian, and diagonalize that one again, because we have here this triplet singlet crossing, for example, now we get fully separated states, and we can see now here that we get different ordering of states, and also the triplet, because it's degenerate here in energy, but it has different spin orbit couplings and also has split in energy. And in the adiabatic representation, NUCs are relatively, so the blue one is supposed to be the NUCs, they're relatively peaked and local, but for example the spin orbit couplings are more delocalized, but in the diagonal representation everything is supposed to be a bit more local. However, often spectroscopists think of so-called diabatic states, where every state has a certain character, like a pi-pi transition, a lone pair pi-star transition or something, which are smooth functions, but they do intersect, right? So the character here stays the same, but the green curve is not always the ground state, right? So for machine learning is very good at interpolation and fitting smooth functions, but fitting anything that has a cusp is usually a problem. Therefore, it is often easier to fit this kind of function with machine learning than functions. And here we don't even see a strong cusp, but often when those are much closer, then this becomes very steep here, the intersection scene. So we need to propagate the nuclear wave package. The option one would be we treat everything quantum mechanically, even the nuclei, and then we have like this nuclear wave package, and to do some approximations, and then propagate everything in time. But most of our algorithms are designed to still treat the nuclei classically, and then we need some mixed approach. And the idea is that we can now choose many different flavors of how we actually now propagate our system in time. For example, we could do this on some weighted potential energy surface. We can kind of have the effect of different potential energy surfaces at the same time affecting the nuclei, weighted by the coefficients of our electronic wave functions, which would be Ehrenfest dynamics, or then, which is probably the most common flavor, is surface hopping, where stochastically or non-stochastically, depending on your algorithm, we have hops between our excited states, and then in order to regain our wave packet, so the quantum nature of our nuclei, we not simulate one trajectory, but many trajectories, and then form statistical averages over those trajectories in order to recover the quantum nature of our nuclei. And then we have we can have stochastic hopping, we can have deterministic hopping, we can have algorithms which do not use non-abatic coupling vectors. There's a whole zoo of these algorithms there. And there's also other branches where for example, instead of hopping, we kind of branch out in order to really follow the quantum nature, and which is then, for example, called ab initio multispawning. But I don't want to talk about more the detail of those algorithms. In general, I will focus more on these kind of surface hopping stuff, but we will really want to focus on the machine learning here, because this is what this workshop is about. So just one last word to surface hopping, just so you can imagine what is really going on. So imagine now we have a ground in a coupled excited, one excited state, and we have now here several structures which we then excite with a light to the first excited state, and then we have different geometries, and then over time they relax, they come to this intersection here, and then stochastically some of them relax down to the ground state, some don't, some stay up in the excited state, and then we have this time evolution here where some go back to this minimum, some are going here to the right, and some are trapped up there and oscillate back and forth. And these stochastic hops are, for example, induced by the non-abatic coupling vectors, and then after every hop, they then follow the new potential energy surf. And all of these equations of motions are solved by various programs. For example, there's the SHAR code, there's Newton, there's AIMS, and there are many more codes out there that all can solve the time-dependent Schrödinger equation. And basically, the whole idea of all of these programs is you have coordinates, you feed them to the quantum chemistry program of your choice, then this quantum chemistry program calculates for you energies, forces, non-abatic coupling vectors, so whatever you want, and then you somehow parse the output, whether that is file-based or you have an interface for this, then you propagate, you solve your equations of motion, you get new coordinates, and so on. And then the clear thing is, just as we do in the ground state, what we want to make cheaper here is obviously the quantum chemical calculations, because they're actually even more expensive than in the ground state, right? Because we are not just solving for one set of energies or forces, we're trying to solve for several sets of energies and forces, and additionally properties as well. So the speed up, the gain we can make by using machine learning instead of using quantum mechanics is even greater than in the state. So what can we do? Right, our model predicts energies on forces of several states, but now the question is, when we get to these intersection seams, which might sometimes be very peaked, the adiabatic surfaces are not smooth, and that's very difficult for models. And we might need special architectures in order to fit those intersection seams well. Then, furthermore, we have these non-abatic coupling vectors, and maybe even spin couplings that we might want to predict. The non-abatic coupling vectors here, so this derivative with respect to coordinates of the wave function and then the overlap of those two, diverges for the conical intersection, meaning it goes to infinity, which is terrible for a machine learning model. Luckily, there is a connected quantity, which is sometimes called SMUX, which has the dimension of a force, and can be written as the product of the non-abatic coupling vector with the energy gap. So one could, in principle, learn the SMUX, which don't diverge, because if this thing here diverges, when those two states become degenerate, this energy difference becomes zero, and therefore usually stay finite. But then we can have to recover the non-abatic coupling vectors, which we need for the dynamics, by predicting this quantity here, and then have also this difference predicted, and then taking the ratio of our predicted smooth NUX and this thing, which can of course also cause problems. And SOX, I'm not going to talk about spin-off couplings that much, but in general there are matrices which have the shape of the angular momentum of your one state times the angular momentum of the other state that couple with, for example, ZOX for singlets to triplets would be a 1 times 3 dimensional matrix, or a triplet ZOX would be a 3 by 3 matrix. But how do we predict those? So There are lots of different architectures and models out there. I think, for example, Pyramid is a bit of an outlier because that is really just a feed-forward neural network which takes Coulomb matrices and then tries to predict these properties. This, of course, has a drawback because it's super molecule specific, because if you have Coulomb matrix as an input, your neural network is fixed to a certain size and does not scale with different molecules. I think the mainstream solution here is the same as for ground state properties. One takes a graph convolutional neural network, architecture like SNET, Payne, Maze, or whatever, and then modifies the architecture slightly in order to be able to predict these properties. And famous examples, for example, are this SHARC or Spain, where people from Vienna have the SHARC code, which is one of those codes that can solve these non-abatic dynamics, and then have adapted SNET and Payne and written interface with SHARC and then gave them these nicknames here. But in general, most of these NAMD codes are super versatile, right? Because they're meant to be interfaced with many QM programs. So as long as you can write an interface for your machine learning model, you can really use whatever architecture you want. For example, there's also other code like MLAtom, which was, I think, in the original also a more ground state based and works together with ANI-type models, but now has a lot of Newton X functions in there so that it also can do non-abatic dynamics. Okay, but now let's get to the actual machine learning part. Assuming now we're gonna do graph convolutional neural networks, and for now, so we only want to learn energies and forces and don't worry about the rest. So we use some algorithm like Zhu Nakamura, Landau-Sina, or now curvature-driven dynamics where we kind of have expressions for the hopping probability which do not depend on the non-abatic coupling vectors. And then usually what people do in the ground state, which you've probably already heard talk about in this week, as you have your molecular graph here, or the graph that happens to describe the environment of certain atoms. Then you have your hidden state. You, during message passing, you craft a new message, you update the hidden state, and you do this for several rounds until you get some final atomic embed. And then you have a feed-forward output layer, which then outputs your atomic energies, which are then summed up over the whole molecule to give you your molecular energy. And the easy thing to do is we really just replace this with several output keys and get what I would call an adiabatic neural network, which then gives me several adiabatic energies for the different excited states. And then the forces are learned just as, in the same way as for the ground state. We really just, again, backpropagate with respect to the input coordinates, our gradients there. So this basically requires almost no change to your underlying architecture, because really you just replace having one output key with several output keys. So, but again, the problem is how do we do the cusp PS? And then the idea is we obtain the adiabatic energies just exactly how we do in quantum chemistry through diagonalization. And here there are several ideas out there. One would be to learn an invariant characteristic polynomial, which is then called, assemble a so-called companion matrix, diagonalize that, and obtain the adiabatic energies. And another one would be to go through an auto-encoder architecture, for example. All right, let's look at the characteristic polynomial. The idea is that we're trying to learn smooth functions here. So our neural network smooth functions, and they're related to our adiabatic energies in the following way. So one term would, for example, be the product of all differences of the different adiabatic states in the mean energy. And then we have these mixed products here of the difference to the mean energy, and then with growing index, these products become longer and longer and longer, until the last one would be the sum of all of these differences, which obviously is 0, because then this just becomes the mean, and this becomes the sum of all mean, and then this cancels out in the last term, 1. So those two do not have to be learned. You have to learn the mean, which is defined to be smooth, and then you have to learn all of these products, which if you have all the important states and no other state that then still interferes, they're also smooth. And when you assemble them in a matrix like this, so you put the learned mean on the diagonal, and then all of these other polynomials here on And to the last column, then you can recover your adiabatic energies through diagonalization. And as a proof, for example, here in this paper, they showed this, that this would be their, for their molecule, their adiabatic states, and you can really see here the conjugate section, which is super peaked. But you look at the mean energy for the same coordinates, then it's extremely smooth, and also the product of those is smooth. Now, rarely are we dealing just with two nicely electronic states and no other electronic states interferes, right? Because there might be, as we had, for example, in one of the first slides, we might have different characters coming in somewhere at a different orientation of our nuclei, and therefore we have to deal with more states in general than just two, and also we might get different characters or different surfaces intersect at different geometries. And this means we might want to have, we might be interested in the lowest 2 or 3 states, but because we have more different spectroscopic surfaces that are relevant, we might actually have to learn a larger companion matrix, even though we're only interested in the 2 lowest excited states. And then they go further on here just to show you that this really works. So they, in this paper, they really compare then how the learning directly the states and their companion matrix, how the companion matrix recovers the cusp as it has to, right? Whereas if you learn it directly, because neural networks like to learn smooth functions, they kind of learn an avoided crossing because it's very, very hard for them to recover the peakedness of this conic intersection. And they did this here for 2 molecules, so one would be an ammonia cation and the other one would be just an ethylene. So very small molecules, on which they then could do benchmark calculations. However, as nice as this sounds, there are problems. Because these polynomial terms can become very large, right? Because if I have 2 excited states, I only have the product of 2 differences. But if I have more excited states, I get more and more and more terms become increasingly large. And the problem is that small errors in the predicted polynomial terms can lead to large errors in the adiabatic energies after diagonalization. And the other problem is, it is okay to learn energies with this architecture, but very hard to learn forces, because backpropagation through the diagonalization of a non-Hermitian matrix incurs usually a phase factor, right? Because which is then undefined, and which will result in your backpropagation to just fail. You can, of course, target the polynomial directly, but this would then limit you to exactly as large a companion matrix as excited states you're interested in, and you cannot account for any higher intruding states. So there's a bit of a here, which is why there was this other suggestion how one could learn energies and forces. And the idea is here very similar. So one would again recover the adiabatic energies through the diagonalization of a matrix, but here the matrix is supposed to Hermitian and recovered from some invariant polynomials. Do these invariant polynomials come from? Well, the idea is machine learning is going to take care of this for us. We, from our quantum chemistry, get our adiabatic energies, and then we'll train an encoder that predicts these invariant polynomials, and then we have a decoder that then recovers again the adiabatic states that we would get from quantum chemistry. And then, once we have for many geometries decent invariant polynomials that are sufficiently smooth, then the idea was, okay, they train now a maze model that then would predict these invariants, and then they only use the decoder part of the order in order to recover again the atomic energies, which then they put together to get the molecular excited states. And so basically, the idea is that you first train this autoencoder and then train the maze architecture afterwards. And so during your training, you have this reconstruction loss, you have the matching the output of the encoder and the output of maze together, and then you also, of course, target the forces in order to get the forces right, because they contain a lot of information. And then in order to prove that this works, they also showed this here at one of the classical benchmark systems for non-adiabatic dynamics, the methyl ammonia cation, and showed that if you do the standard, so you learn directly the energies and forces with no special architecture, you have a huge crossing, and if you use their architecture, you get a less strong voided crossing. But because we're not strictly learning something thematically strict here, but we're trying to use machine learning in order to predict these invariant polynomials, which we then again diagonalize, it is not as let's say, quote-unquote perfect as the Caractères polynomials. However, it is also more flexible and breaks easily. And because it is meant for these conic intersections, it was just called X-maze. So it basically is maze for most of it, and it really just has a slightly different readout layer here, together with this attached decoder to convert the invariants that are predicted by the readout layer again into the end. So, but now we might want to say, okay, we don't want to use an algorithm that just focuses on energies and forces. We might want to get also coupling vectors. So, training directly on non-adiabatic coupling vectors is almost impossible because they can diverge. Smooth NUCs are, but there is still the problem, because if I learn the smooth NUCs, I will need to divide by the energy gap, and if I make some small error in the energy gap, which already is supposed to be small, it's in a very large error in my NUCs. And then the next question is, how do I set up learning NUCs, which are in principle that rotate with your geometry? So if you have an invariant architecture like Pyramid or Schnark, you can only learn NUCs by describing a gradient of some fictitious potential, which they're not, but that's the only way you can recover vectors in those models. And so in principle, NUCs a pro component which a gradient field does not have, but it is still a decent approximation. And then you can go, okay, as soon as you have an equivariant model like Spain or Maze or whatever, you could non-adiabatic coupling vectors directly. However, it would be way too easy if any of that worked, because NUCs are double-valued functions. To do with a Berry phase that is attached to these wave functions, and the fact that the left and right function the same, right? Because usually if you look at the energies and the eigenfunctions of the Hamiltonian, you only are interested in the properties which are on the trace of this matrix, but here we're interested in two states interacting with one another, which means that for the same geometry, you can have this, depending on the degree of your trajectory, you can have non-adiabatic couplings that point in the opposite direction. And only so if you are at the same point and you come back to the configuration twice, then you recover the non-adiabatic coupling vector that you had in the first place. Which is another thing we have to worry. Luckily, it's really just a sign change. So if we figure out a way to learn these in order to make sure that we don't care about the sign, like sign of the vector, then we're good. But it's something that has to be taken care of. That means we either need to adapt our loss function or our architecture to take care of this. So the easiest way, or the first way, was really just to say, okay, we learn the NUCs directly, but we have a phaseless loss, meaning we try to keep the phases all predicted states correctly, and therefore this becomes a combinatorial problem. So we have our NUCs that are from quantum chemistry. We have machine-learned NUCs, and then we multiply them with -1s or 1s, depending on which phase we assume our states have relative to one another. And we do this combinatorially for all the states that we have in our loss. And then we take whatever one of these mean squared errors is lost. And then we say that is the combination of phases for my data point. That is relatively expensive. It's expensive and doesn't yield much improvement. So recently people have gone over to just say, okay, we'll just not be correct and really try to figure out what the combination of all phases for different states is. We really just worry about one set of states, A, B, and do them, and then we do the next set of states for the same geometry. So it's really just comparing the difference or the sum of those and then taking whatever is smaller as the actual loss for this configuration and for this combination of two states, alpha, beta, instead of worrying about different states at once, which also works reasonably fine. So another idea is, because NUCs are double functions, is that our machine learning model is going to predict something that is independent of this of the sign. Here, Jeremy Richardson from the ETH said that our machine learning model, instead of predicting the NUCs directly, actually has to predict this matrix gamma here, which can be written as the outer product of our smooth NUC with the trace removed. So, and if we then diagonalize this matrix gamma, which is the actual output of our machine learning model, then we only have one with a non-negative eigenvalue, which again is our smooth NUCs that we're targeting. So it's very easy to pick out, right? Because all the other ones have negative eigenvalues. We take eigenvector corresponding to the non-negative eigenvalue, and we're good. And then we would target, for example, this smooth NUC here with a phaseless loss in order to, because through this architecture we have lost any information about the sign of the NUC. And that works again molecules, but the bigger the molecules become or the more configurations you're trying to learn, the NUCs are still, even though there are all of these adaptive lines or even these architectures out there, it only very little improves the actual error you're doing on learning the NUCs. The next step, okay, we have architectures for learning energies and forces. We have ideas for learning the NUCs. Maybe we can learn something that combines energies and forces together. And there was that we're trying to target the diabatic Hamiltonian directly. The problem is the diabatic representation is not unique because we have non-orthogonal eigenvalues or eigenstates. And in principle, you could do any kind of diabatization. The idea again is we don't figure out our machine learning model is going to figure out the diabatization. We're just interested in diagonalizing that and recovering our energies and forces, and because we're learning the diabatic Hamiltonian, also all at once. So again, in the adiabatic representation, our ground state would be, for example, this blue state here, and then the state would be the red state, and they're all off-diagonal elements are 0 in the MCH representation. However, in the diabatic representation, we not only have here the two diagonals which are now smooth and cross each other, but we also have these off-diagonal elements. So the idea is that now our machine predicts some full matrix HD, this one here. And then if we diagonalize this matrix HD, we actually, on the diagonal, we recover our energies. And if we use the same diagonalization, so the same matrices, and apply these to the matrix that is filled with the gradients of this matrix, then we get our the gradients or the negative of our forces for the diagonal elements, and the off-diagonal elements happen to be our non-adiabatic coupling vectors. So basically our model now predicts this matrix HD, and then the loss targets the outputs of this diagonalization, and because HD is Hermitian, it's easier to implement because it's a symmetric matrix, and the algorithms for diagonalizing that are much more robust. And again, if you have intruding states that have a different character and become, so basically what you can think about is you have now some other state here coming from up here, and then it becomes maybe the ground state later, But then to have all the diabats together, you need also to have learned this smooth state here, even though you're only interested in the first two, in the two lowest ADAs. And this, for example, was implemented with the pane architecture in this paper. So this is again the pane architecture. You have the readout layers. The readout layers predict these different diagonal and off-diagonal terms of this matrix. The matrix is assembled, and then it's simply diagonalized. So for SOCs, they are supposed to be smoother. However, they appear, but in general, they're complex valued functions. They're also relatively difficult to learn, and as of yet, there is no architecture out there that has any special architecture to learn them, like NUX or Forces, because most people actually just focus on singlet states, and therefore you don't need any NUX. But I'm saying yet because I'm pretty sure there are in the next years there will be some architectures that do that. So the question, all of these architectures that have this common theme of we're trying to predict something and then we diagonalize this in order to do better and be closer to what quantum chemistry actually does, but how good architectures? And here we're going to compare from two, this is from two papers. One would be a Spain model published last year, or again the methyl ammonia cation here, and it compares Spain and SNARK. And then we have here this diabatic artificial neural network, which is a pane type model, which tries diabatic representation. The problem in comparing all of these things is, unlike for ground state, there is neither benchmark nor is there a data-upon system one should look at, right? So here, they have chosen kind of this benchmark system that is well known in adiabatic dynamics and a high-level theory, but then these applications are always, or inventions are not only just inventions of new architectures, but they immediately target at certain applications. And so this one here was targeted in doing non-adiabatics for azobenzene derivatives. So these are thousands of different azobenzene derivatives, and the level of theory was spin flip TDDFT. So comparing those is difficult. I compare those to the same kind of error in order to have some meaningful comparison. Then we see, for example, here that Dan has a larger state averaged MAE in the Spanish SNARK model for the small one. But then again, this is for the entire molecules. And if we would say a per atom error in energy, then this one more, because the azobenzenes have much more atoms. However, since these are different derivatives, it's very hard to give like for me, who did not write that paper, to give you an per atom error, because they have varying atom numbers, and I can't tell you what the average number of atoms is. Then, however, something that should be independent of the size of the molecule is the energy gap. And here, for example, they just didn't publish what the energy is. In general, these errors in milli-electron volts, you can also try to convert them to kilocalories per mole, are much larger than what you would usually accept for ground state. Also, the force errors, especially here, is at least a factor of 10 too large. However, because all of this is relatively difficult to do, people and roll with it. And then to compare NUX here is also very difficult, because here the people put the state average errors for themselves. Here it's the smooth NUX, where we still would need to divide by the energy gap. And again, I don't have that data. But in general, especially if we look at the forces, this error is relative for especially for these models here, but also for this one. And then again, it's hard to compare to say, okay, those models are worse because they are fitting more detailed level of theory, where already maybe spin flip TDDFT is easier to fit, but it already introduces errors itself. So it's very difficult to distinguish what the strengths of the model are, what comes from the set of molecules they're looking at, and what the level of theory is actually helping when trying to compare these different models non-adiabatic dynamics. And as another example why things are difficult to disentangle, we recently did an application for molecule excited in water, so we did MLMM simulations for photo excitation, where we have the small molecule here solvated in water, or really just the small molecule is the QM region, and then the water molecules are the MM part. And what we did is we ran a lot of simulations, we got data, and then trained different models, and just compare the different models. And the only difference between these models is, for example, the initialization of the models. The training split completely the same. And what we then had, we had this holdout set of trajectories where we have the initial conditions, so initial initial velocities, initial geometries, which are identical, which we then ran with machine learning and which we had run with the ground truth. And when we look at this, we have 3 different models which have the same training data and only differ in the initial weights. And here the dashed line is the ground truth, which should be approximate, and then model 1 and model 3 optically relatively well reproduce the ground truth. However, model 2 is far off. In principle, for any meaningful application, you have no access to the dashed line because you're doing machine learning in order to tackle a system which you usually could not tackle, right? Because it's so large that it's visible to non-adiabatic dynamics brute force. But, and all of them had basically training errors that were only if you start really digging into and looking at things that go beyond root mean square error with respect to energies and forces, you are able to ferret out that model 2 might be less than model 1 or 2. But how this then actually translates to dynamics, which you're really interested in. And non-adiabatic dynamics are non-equilibrium dynamics, right? We pump energy in our system by photo-exciting it, and then it kind of de-excites within hundreds of femtoseconds or a few picoseconds. And then basically we have put more molecules, energy that is on the magnitude of 300-400 Kelvin temperature, right? That really, how then small errors, the energy gaps, and so translate to very different dynamics is very difficult to predict. So, to summarize, there are many special architectures already account for cusps and to make it easier to fit several PESs at once. NUCs and SOCs are double-valued functions, meaning that you can have different signs depending on the phase of your wave functions when you do quantum mechanics. NUCs and forces can be combined, for example, in space like DAN to be predicted all at once, but so far none of these models, none of these architectures, in my opinion, really reach the quality or the error margin of the ground state models, like the foundational models that have, for example, that have been developed, even though foundation models are trained on lower level of theory, need to be refined for application, but in general, there's still some catching up to do. And when one performs active learning for these molecules, one really should focus on the parts of space that are important for non-adiabatic dynamics, right? People should start focusing more on the conic intersection seams, and the training loss also should not be forces and energies, but it should really highlight those regions without overly neglecting others. And then, in order to really understand which of these architectures work better, there should be a fair comparison of all of these approaches. So maybe same data set, same messy parsing model, and then we have just different output layers, etc., so that we can really understand which of these suggestions work well and which do not. And with this, I want to thank you for your attention. I want to thank the organizers for inviting me, and if you please go ahead.
Thank you. Just a curiosity, I mean, because a single trajectory in non-adiabatic dynamics doesn't have a lot of meaning in principle, because you need to have a set that. I mean, would it be meaningful to switch completely framework and instead of fitting to single trajectory, try to learn in a more collective way the behavior of without trying to simulate single trajectories? Is a general question. Like, if there's any other completely different attempt in this sense.
Does it work? I'm not sure I get your question because, as you said, right, like you need to simulate lots of trajectories in order to recover the wave packet, right? Like, and I don't think there's, when a trajectory is just not going to do this as long as you do a single trajectory where your nuclei really are just on one point. If you say, okay, I'm going to do MCTDH, where my nuclei are actually a real Gaussian wave packet, of course, right? But then the dynamics become also much more expensive and have to be run very differently from how we run traditionally dynamics, right? Because in principle, electronic equations of motion, and then it's really again velocity Verlet in order to move your nuclei forward in time.
Any other question?
Could you maybe spend like a few minutes saying what are the problems doing similar directions for solids or for crystal structures?
For crystal structures?
Yeah.
Well, non-adiabatic dynamics in solids is usually done a bit differently or more approximatively, because there people often, what they do is they take a ground state simulation, just run a ground state simulation, and then post that simulation, go back to the beginning and say, okay, actually been excited into some excited state, and only basically following those nuclear degrees of freedom, then simulate the dynamics of the electrons. Say, well, if these PSs are so similar and my kinetic energy is so strong because I have such a large bulk material compared to the energy of the photon that it doesn't want nuclear degrees of freedom at all, right? And so they really just, they kind of do non-adiabatic dynamics, but they don't have fully this interplay electronic and nuclear degrees of freedom. They first do their nuclear degrees of freedom, our trajectory, and then run the electrons again. Whereas for all small molecules, it's done more accurately. One affects the other the whole time, right? And as people are working on this in order to improve this, but the problem is that for three-dimensional materials, very difficult to get excited states and all of these properties in general. Like, yeah, like for example in VASP, there have, as far as I know right now, working on getting excited state energies and gradients, and we're not talking about NUCs at all yet.
Any other? If no,
can you give us a few details? I didn't fully understand what the model is learning, if the different energies are learned separately, like this excited the energy ones, and if instead the loss is comprising all of these or not. You showed, I think, in a form of the loss.
Sorry,
So here, yes.
But so this is a special loss because here you have this reconstruction loss for this arc. But in general, people train this the standard loss, right? You have the mean squared error for energies. You have the mean squared error for forces, for example. It's just not one state, but it's several states at once.
Okay, and so the forces are also for a specific adiabatic surface.
Exactly,
okay. And you weight them in the same way. So, in the sense you are going to have different contributions.
So people exactly, give usually like forces a stronger weight than the energies, right? But then people have also added that on top of the energies and forces then also targets the energy gap specifically as an additional term. So I don't think there is the one loss function out there for models, but they're all similar and they're not, as I said, tried to say in the last slide, there might be need for some improvement with regards to loss functions.
Okay. If there are no more questions, I think we can go for the tutorial. You know, if you need a minute.
Yeah, I was reminded that you all should again for today, if you haven't done so. Okay, so in this tutorial, we're going to talk about or try to compare two different architectures, namely the Schnark and the Spain architecture. And so the architectures that are developed in Vienna, and I'm currently stationed in Vienna, so I thought I'm going to try out the in-house architectures. And the molecule we'll be looking at will be the infamous cation. It is a for historical reasons, a good benchmark system for non-adiabatic phenomena. The properties of the different PS are very easy to understand, and it's a small molecule, so therefore we can really probe the different degrees of freedom. And so in the first notebook, you can really just get familiarized yourself with the molecule, and what we've prepared is basically a set of geometries that present then of different, like a scan along a bond, a scan along a dihedral, combined into one set of geometries, which we then can subsequently analyze and do the ground truth. And I'm just gonna run the notebook just like you are, and I guess the imports are the longest thing here in this notebook. Okay, I mean, a little bit of what is happening. First, we import all the necessary packages. The configurations are stored in an ASE database, where everything is saved in atomic units, including the geometry, because this is what the Spain and Schnark and Spain architecture were made to work with. However, basically anything that usually visualizes geometries works in angstrom, and therefore go over this database and convert everything to angstrom and able to look at the sets of configurations. And here is this molecule, and you can see that we basically rotated the dihedral, and then, so if you look at this, we rotated the dihedral always from 180 to 90 degrees, the metric, so we don't need to go longer than this. And what we also did is we pulled on the central bond until, so giving us about 9,000 geometries, so we can do a very fine scan of the potential energy surface. The data that we've trained the models on is from a paper from 2020, which contained about 4,000 data points. So the data set this is trained on is not even as fine as configurations we're spanning here. But it's just so that we have a freely accessible data set to everyone. And here we look at the, so this is the ground truth, right? This is the ground MRCI truth. So the level of theory, this model was trained, and then you can already see even the ground truth for excited state is not always reliable, right? Because you can see that there are definitely some very strong non-smooth, we can like see here and here where the solver definitely converged to very different solutions all of a sudden. So if you scan such a large amount of data, you can't just always trust your quantum chemistry black box. And this is a data set that was Spain model. So I made this interactively, so you can, it's a bit slow, but you can try to pull and get a better feeling for the potential energy surfaces. And yeah, so you can, for example, see that we have here one conic ground set in the first excited state for this 90-degree angle when we rotate the bond, and if we pull very much on the bond, then, for example, the first and second excited state get very close. Yeah, the thing is, with this data set, these models, training these models like any other model training takes its time, so that took too much time for this tutorial. So we pre-trained them for you, and now in the second notebook, you basically take the models and you're going to do predictions for those models, for those 9,000 geometries. And take some time to read the documentation, and because, I mean, in principle, there's no going on here in this notebook, but if you're not familiar with the SNETPEG architecture, then feel free to take your time. Yes.
You didn't get full. I did. Okay, then you didn't run maybe the very first cell in the notebook 02. The very yeah. So this one should be very soft. Yeah, okay. This line is supposed to fix exactly that.
I think you have the same problem. So that everyone knows what's going on. So we wrote these tutorials just for CPU usage. Resources would be available for everyone during this workshop, but it is relatively slow since we're trying to predict for 9,000 geometries twice, and therefore ported everything to GPU, but which doesn't seem to be working for everyone for some reason. Which is like this, right? Like you guys have like an additional cell here on top of the in the version which you just git pulled, which should be with the GPU version, but for some people this creates an error, which is not a problem because whatever is predicted here, we've already put into the directory. So even if you for some reason can't run this notebook, the results of this notebook are part of the tutorial. So what happens here? In principle, relatively straightforward. We set up a ASE calculator which loads the specific model. In the top there it's the Payne or Spain model, and here it's the Schnedt model or Schnark. I mean, in principle it's a Schnedt model that is just predicting more than one energy, right? But for marketing reasons they decided to in Spain. And then we connect to the database on configurations, set up vectors for the energies and predicted NUCs, predict energies and non-adiabatic coupling vectors. I mean, we also predict forces, but we're not saving those, and then store them in this NumPy array. The same for both models, so we can really then dig into the predictions and compare. And these models, as because someone asked about, they were trained to predict energies, forces, and then non-adiabatic couplings all at once, right? So this is one model that predicts all these different things. And I think the most interesting part is notebook number 3. So even if you couldn't run number 2 or it's still running, shouldn't matter because everything in 3 should be on its own. And now in 3, we're really going to try to do a deep dive and dissect the different predictions of those models. So at the beginning of the model, you have a lot of like imports and also parity plot for excited states, which you can look at a closer look later. Also, as a bit of information about the models, and I mean, in the folders that contain the models, you can look at but just as an information, they both have 3 layers of message passing. They have the same cutoff radius, and I think, if I remember correctly, they 28-dimensional embedding vectors. So the only difference really between those 2 models is that Paine also has equivalent. Schnet does not. And if we now compare the predicted potential energy surfaces, like macroscopically, then we can see, for example, that this non-smooth part here from the ground truth was totally smoothed over by Schnet. The Paine surface is a bit more ruffled, but in general also smoothed over those things here, which are also not correct, right? Like they come from the this converging to a different solution. And in general, like the closeness here of the ground state and the first excited 90-degree angle of the bond is somewhat is there, this feature, and then the first excited state and the second excited state start pulling on this bond is also correctly reproduced. So all in all, we can kind of say, okay, the potential energy surface look okay. The Paine one seems a bit less smooth than the Schnet one, but because we have more features, right? And we had a bit maybe contradicting data, which we try to adjust. In general, overall, this looks okay. Now, we might want to zoom in and see how good or bad is it truly. So, and here, for example, we're looking at the energy gap between the ground excited state. So, we're looking at the energy difference of this and this surface here. So we're expecting up for large angles and a large gap for small angles. And then here for this top corner, we just quantum mechanical data, right? So if we look here at the bottom, it generally fits, right? So are reproduced okay. But if we now zoom in further and actually look at 1D slices, where we then really would see these conical intersections, things don't look as nice anymore, right? So now we have here our quantum mechanical data, which produces exactly this cusp we talked about. So we have our first and second excited state here, for example, in this slice, because we're looking at along the bond length, and both Paine and Schnet created crossings, right? So they predict a relatively large energy gap here between those. And you can also see that the minimum on the second excited state is to a longer bond length where it shouldn't be. And this is milli-electron volts, right? So this gap should be 0 at this point, and it's overestimated to 300 milli-electron volts, so we're like 20, 30 kilojoules per mole off at this point, which is considerable. And then if we look at the other conical intersection for the twisting geometry, it gets even worse. So we have here, again, now data problems, but if we really just focus on this point, again, we have this intersection of those smooth lines we've talked about before, but if we then look at the adiabatic energies, they touch structure there, and the models don't even look close in what they should look like. Even though if we zoom out and look at the full surface, it looks kind of okay, but if we now look at 1D slices and really focus on these cusps, these models look vivid. And we can even see that, right, like here, for example, the pain model for this specific geometry, it's off by an electron volt, which is crazy. So, of course, these models are not perfect. The hyperparameters are not optimized. The models might be a bit small, and also there is some, the data set might also not be the best to critique, but I'm just trying to say an adiabatic model which has no special features and really just tries to predict these adiabatic energies and a lot of things at once, right? It's trying to do several adiabatic coupling vectors at once. There is trade-offs going on in the loss, and if you don't have specific data here forcing this, and maybe you don't have a data point here, but a way where they're actually closer to the ground truth, then it's just not gonna fit that well. And there's nothing in the architecture, because these are these adiabatic models that would force this to have a cusp, right? So I also want you to understand this notebook really as a critique on these models, that even though they're somewhat state of the art is definitely not good enough to what we're actually trying to represent. Is this clear what we're doing?
So, like when we want to reproduce, for instance, the structure, the phononic band structure, one learns directly the full matrix and then diagonalize it a posteriori, and here instead kind of learn the different surfaces and the couplings and so on and so forth. I didn't understand, don't just try and learn everything and then do a posteriori the... Yeah, but then the behavior, especially if you have something that is not smooth, the behavior... Okay. Yes. Yes, exactly. And then you said, okay, but then there are the non-adiabatic, which is like... Okay.
Some of these papers have not published the data sets. I've just worked with public data, right? And because right now in Vienna, people have like published this model, I could just ask the author of this model, hey, can you train a model for me for the workshop for this one? And what I wanted to highlight is really that just if you have an adiabatic model and probably also data set that is just generally somewhere and not has specific data at these cusps, right? Because these cusps, if you come with a trajectory, you pass through it very quickly, and most of your trajectory is actually spent before or after, but not at this critical point. So if you do a trajectory and get your data from there, you actually have very little data at the points that are actually very interested, right? This is what I'm saying. If you do active learning, you should really target those areas so that you have more data where it matters. And yeah, those were also trained with normal loss functions, so it was really just a mean squared error loss. And maybe we also should really emphasize in the loss that when the energy gets small, that we should give those frames a higher weight, right? But yeah, I agree with you. But then again, just getting more and more states, right? Like the question is, how many states are you interested in, and how many of these spectroscopic states are relevant for the geometries you want, right? Because those might be a different number than the adiabatic states you're interested in. And then, yeah. And quantum chemistry is always going to give you adiabatic states. All right, now we also want to look at the non-adiabatic coupling vectors. The problem is, for every single geometry, a non-adiabatic coupling vector is a 3 times number of atoms vector, which we can't really visualize in any kind of cut or whatever, which is why we kind of took the norm along x, y, z, and then kind of just summed across the vector. So basically every point just symbolizes, is the NUC large or is it not large, right? But not where does it point towards. And we would expect that at regions where the surfaces intersect, so where the energy gap gets small, our gaps get NUCs get large, and vice versa. And again, we're now really just loading, taking our predictions from the previous notebook and try to make pretty plots here. And again, ignore this here at the top, because this is definitely where I would not trust the ground truth. But we have here this region where the ground state and the first excited states intersect, because this is where we have the 90-degree angle between the 2 parts of the molecule, and we can see here that the non-adiabatic couplings vectors really become very large compared to everywhere else. And in principle, so this is the large area for the ground truth. In principle, that they're large here is somewhat also done correctly by Payne and Schnedt, but because we're looking at the NUCs right now, and they predicted the smooth NUCs, and their energy gap is way too large. They're predicting much too small non-adiabatic coupling vectors here. And also interestingly, even though there should be no big NUCs in this region, this one a little bit, and Payne even more, wants to predict larger NUCs in this area, even though they shouldn't be there. And if we now try to really not just like visually compare errors, but really look at error statistics, we can also do that. And here we, for example, look at the difference between the energy and the ground truth, and we can see that if we just look at energies, even though we had some regions where Payne in total was worse, or was definitely not better than Schnedt, overall, on the surface here, the errors are smaller for Payne, which is nice, because we would hope that an equivariant architecture would in general be better at understanding molecular geometries and everything. But when it comes to, and also when it comes to non-adiabatic coupling vectors, we also can see that the Payne model might have a bit more white, meaning a bit less errors. Don't really interpret anything in these weird lines. This just has, I don't think there is anything really magical about those. This is just where, for some reason, the model was very close to the ground truth, and in other areas it wasn't. But I would not go so far as to, and these white points, I think I've written this in the markdowns, but I haven't said that yet. The white points is just where we don't have any, where the ground truth calculations just didn't converge, which is why we don't have any data there that we can take differences with. And to conclude, because I mean machine learning analysis are nothing without parity plots, we're also really just gonna look at the test set. Now we have compared all of these. So for now, in this notebook, we really compared our predictions with the ground truth for this 2D scan. And here in the last part of the notebook, you can compare the test set and the models with one another. And here again, we kind of then load the model, we load the data set, so it was trained on. We take the indices for which were the test frames, we do the predictions for those frames, which are just 400, not 9,000. And then we look at the test statistics. Okay, I hope that everyone was able to run this third notebook and that there are no CUDA problems for most of you. Yeah, so basically what we're looking here are the parity plots for the test set for both of these molecules. And within the first row would be the energies, the second row would be the forces, and then the third row we're going to look at in a second would be the non-abiotic coupling vectors. And for the energies, well, because they're excited states, so with every further excited states, we see points lying higher in energy, but we also see the error increasing with every excited state, which is very typical because they're not necessarily harder to fit, but the ground truth data is just arguably worse. And therefore, we're also testing against data that just has inherently a larger error. Because with every excited state, we can just trust the ground truth also less and less, unfortunately. And then we kind of see the same pattern with the forces. And I'm not sure what your favorite unit is, but I would say for forces, usually acceptable errors would be in the tens, or like at least only 2 digits for milli-electron volts per angstrom, and definitely not 3 digits. So I would argue that the force errors are definitely too large, but again, these models are trying to balance many things at once, which is a bit of a problem. And then if you look at the non-abiotic coupling vectors, that's a bit of a tragedy. I mean, we didn't really accept SCHNET to be very good at those because it's learning them as a gradient of a potential that doesn't really exist. And there is some correlation here, right? The Pearson correlation coefficient is not 0, but it's not anywhere close to 90. And your coefficient of determination for all of them is negative, which is really not something you should be aiming for. When it comes to numerical values for MAE or RMSE for NUCs, I don't think that anyone has a good ballpark number of what is good and what is bad. Which is why, first off, I would really just look at these numbers, and as long as R squared is negative, your model is not doing so hot. And then if we look at pain, we see comparable errors with energies and forces. There really isn't much difference. And we see slightly better performance when it comes to the non-abiotic coupling vectors. Here, for example, we even have Pearson correlation coefficient from 0.82, but again, the coefficient of determination is negative throughout, which definitely means that having an architecture that just tries to predict the properties of excited states directly, which a lot of architectures do. So what I showed you today is like, these usually are papers that have only been really used once ever. But most models that do a machine learning for excited states really just go this adiabatic route and predict energies, forces, and maybe non-abiotic coupling vectors directly. And as you can see, this test statistics, it's really not good enough. Even though for ground state properties, where we really just look at one state for energies and forces, this works well. But if we try to use the same approach for excited states, it really just isn't good enough. And this is why we definitely need better benchmarks, and also the last word of what a good architecture for excited states and doing all of this has not been spoken. And then I want to thank you for your attention.
Yeah, thank you very much for the very nice talk. So I was wondering, do you expect that also, not for this case because these are small molecules, but sometimes excited states are way more non-local than the ground state? Sorry. And so,
can you say that again?
The excited states are more non-local than the ground state. So does it make the harder task for local models to learn it? So you could have excited states that have completely delocalized state across the molecules, and
but what do you mean by the delocalized? Isn't like the electron density, or what?
Yeah, the electron density is completely delocalized in some excited states.
Yeah, I mean, but in principle, right, all of these models don't know anything about the density, right? They really just know something about energies and forces.
Yeah, but the forces could be non-local in a much
Yes.
more pronounced way than the ground state.
Well, I mean, some people, like, I think I saw a poster yesterday where people learned really totally different models for ground an excited state, right? So then if they're very different, this might help. But then at the same time, I would argue it doesn't help because the chemistry, for example, like your message parsing part wants to learn about should be the same. And really, you should, like, the difference in the different states should go into the output layer. But
Okay.
I can't really tell you how the density is distributed, how this would affect the output. I have no
Yeah, it will be interesting to look at. So we do these kind of plots where we look at the locality of the forces from the FT, and then you can look at the typical decay. And if that's way more long range, like it decays much more slowly for the excited state forces, it will be interesting to see.
Any other question? Sorry.
So I have a technical question. Do you predict all three states at once, or are they like predicted separately and then?
Here in this model, this is so. So this one predicts everything at once, right? Like, it has like one output layer for energies where you have like 3 heads, and then you have a different output layer to get this vectorial property, which would be the NUX, right?
Okay.
But it's the same message passing embedding, which is then fed into different output layers.
Okay. So, but if you would want another like excited set, then you would need to refit it basically, or at least one head and add an additional head to this.
Yes.
Okay.
Any other? Okay, I think I don't see more questions. Let's thank again Johannes. And now it should be time for coffee break now. See you at 11:15.
Yeah, thank you, Hannes. I think it went very well. Actually, the issue was for people who maybe installed something they shouldn't have. So
Okay, so it had nothing to do with it.
yeah, it worked for I think majority of people. So yeah, thank you very much.
Thank you for the additional line. Right?
Yeah.
Hi, thank you for the presentation. I wanted to ask you, can I have your slides? Because I'm interested in what you do, and we will also.
But I mean, most of this is not from me, right? Like, I just summarized.
Yeah, but I also wanted to have a look at the references and stuff because I'm not expert in monodiabatic molecular dynamics, but like in my group we study compensation on the Wilberforce times.
Yeah.
By the way, everything is also on YouTube. Oh yeah, I can.
Are we going to put the slides somewhere?
Processes you can simulate with this, like exciting one single electron in a molecule, of course, or more than one electron.
Just so one photon excitation. I mean, it doesn't have to be one electron, but one photon. Right? Like a double photon excitation is good.
Okay, so basically you can describe like a radiative decay that from
No,
one
no, no.
electron.
This is mainly non-radiative. Because I think, in principle, you could also do radiative decay, but most people, for some reason, don't do that or are not interested in because most people are interested in, at least in our group, are interested in photochemistry, meaning the one non-radiative decay because the decay then
Okay, I think we can start with the next session. Before that, few announcements. So for today, for lunches, the coupons are here, so you can just take them when you are leaving. We'll also try to make a photo before. And so try not to escape. And I think that's it. Later I will tell you where is the dinner. So let me introduce our next speaker, Lukas Popa. Yeah, the title is there, so please, you can start.
Okay, thanks, Ivor, for the introduction. Thank you, Ivor, and all the other organizers for the invitation for this great school and in this nice place. We're enjoying a lot, learning a lot. In this, so in case we didn't talk to you, my name is Lukas Popa. I'm coming from the Fritz Haber Institute in Berlin, Germany. And in my group, we are developing AI concepts and methods and applying them to computational and experiments. So what I want to show you today is some of the methods that we are discussing and some of the concepts we are working on, and with some recent applications. Before I start, I wanted to ask actually two questions. I'm curious about how popular these methods are. So first, can you raise your hand if you have heard about symbolic regression before? There are some people. How about subgroup discovery? Subgroup discovery. Yeah, I see two hands. Yeah, that's good. Okay, good. So this answer is going to change at the end of the tutorial. Yeah, and I hope that we can resonate a bit. And also, I'm looking forward to your opinion about that, about this complexity gap that we were discussing in this panel session. So I think many of the presentations we have so far were using machine learning to simulate something that can be calculated by DFT. This has the assumption that we are interested in something that we can evaluate with DFT and with atomistic simulations. What about if this is not the case? What about a materials property or materials function that we simply cannot an atomistic simulation? And the answer for that, in our opinion, is to use systematic experimental data. And that's what I'm going to show you in this presentation. So let's go. I will illustrate this concept in the context of heterogeneous catalysis, which you can imagine is a key technology for chemical energy conversion, because we want to store the energy that is captured using renewable sources, for instance, the sunlight. So we need new materials. We need materials that are composed by earth-abundant elements. However, there's a problem here. The problem is that the catalytic performance is an example of a materials function governed by an intricate interplay of many different processes. So one or two processes, there are different processes and they are coupled. So let me explain what I mean. So catalysts are materials that will interact, whose surface will interact with molecules and transform into products. So we are typically interested in at least two criteria for a catalyst material. The first one is the activity, so how much of this reactant is going to be converted to product. Second criteria is the selectivity, so which type of products are that we are producing. And normally we want an active catalyst and a selective catalyst that will only produce one specific product or product. So because this is a surface phenomenon, there's a lot of discussion about surface reactivity. So if you look at the literature in heterogeneous catalysis, you will see a lot of papers discussing surface reactions that form and break bonds in these molecules are taking place. So we discuss a lot the energy, absorption energies, and so on. However, this is not all that happens when this material is introduced into a reactor. There are many other processes that are taking place there. So for instance, when the material sees the reaction mixture and the reaction environment, it will react to that, and the solid state chemistry will adapt to this chemical potential. So we often see restructuring of the catalyst material during the reaction. So this is very complicated and often unknown, because it only happens when the material is inside the reactor during the reaction. And this happens in a different time scale compared to the surface reaction. So we have different time scale here. We also have other processes like sintering of catalyst particles, where this, so we often have metallic particles supported on oxides. It's very thin of catalyst material, so these particles might come together and form larger particles. We also have transport that occurs at very different scales, and especially we have reactor transport that occurs at much larger scale compared to the scale of the surface reactions. So I hope this is clear that this is a very complicated materials function. So what can we do to handle this? So first we can think about atomistic. So this is the idea of the multi-scale modeling, where we start from the electronic structure, we have an atomistic simulation, and then we go beyond that using statistical mechanics and linear dynamics here to handle all of this complexity. However, I think it's fair to say that today it's impossible to have an atomistic simulation where we can actually predictive power determine the performance of a material in terms of activity and selectivity. So there's a lot of ongoing work, and we know actually very well the pieces of these processes. However, modeling this coupling of the different processes is extremely difficult. Many people are working in using machine learning to accelerate that. I think we are going to have an answer in the next 3 or 4 years. What was the time scale from yesterday? So what else can we do? I mean, we cannot wait too long to fight climate change. What else can we do? And so the approach that we are working in my group is to actually not doing an atomistic simulation and trying to predict the performance, but we want to identify correlation materials in consistent experimental and theoretical data. And we want to do this by using artificial intelligence, because then we have a chance to capture all the complexity. So let me explain you how it works. So the first very important block here is this systematic experiments. So these experiments will synthesize a material. So in a very way, we'll characterize these properties of these materials, for instance, the structure or the electronic structure, and then we'll test the performance of this material in a certain application, in this case, catalysis. So here it may sound trivial to you, but we learned from collaborations with my experimentalist colleagues that this is completely untrivial for the case of catalysis. Small details on this synthesis or performance will change completely the result. So let me give you an example. So here we are looking at this material. Here it's a metal oxide applied in this reaction, so it's not important, the reaction. And here we have the conversion, so reflecting the catalyst activity. And here in the y-axis we have the selectivity, one of the desired product. And here I would like you to look at the two different curves that are measured using different experimental procedure. So in this first curve we start by measuring the selectivity and conversion, and then we increase the temperature to 400, and we obtain this conversion selectivity curve. So this is the result. However, if we start the experiment temperature 400 and we reduce the temperature, we have a completely different curve, and the selectivity went up like in a significant amount. So what's happening? So when the material needs to see some temperature for it to restructure and transform to a different material that will actually catalyze this reaction. So from here, the reaction conditions are crucial, and this is something that we can hardly model in an atomistic simulation. So in this paper here, we describe standardizing the acquisition of data in catalysis and really keeping track of all of the procedures since the synthesis to the catalytic testing. Yeah, and this applies for other materials properties and functions. Okay, so then we are theoreticians, so we want to also include some atomistic modeling. So the second step of this approach is the atomistic simulations that will look at model systems. And here, I think it's very important to say that these systems that we use to obtain some information, they are model systems. So they are by no means representative of the whole process. They contain some information on, for instance, the catalyst before the reaction and so on. So with using these simulations, we can evaluate some properties of these model systems, and especially simulations to get some information on the environmental effect on the material, which is very hardly measured by experiments. For instance, it requires some special kind of spectroscopy, for instance, and so on. So we want to use DFT calculations here. Okay, when we have done these experiments and the simulations, then we can create a consistent data set that contains, on one hand, a target of interest, which is the performance that we measure experimentally. So please note that the target here is the performance measured under technical conditions, relevant conditions, performance measured by the simulation. So this is, for instance, activity or selectivity. And then we have a lot of what I will call candidate descriptive parameters, which are going to be our used to model this performance. So these are measured by, for instance, these characterization experiments or calculated by these atomistic simulations, and they will reflect underlying processes. That's why we call them candidate descriptive parameters. So why do I write candidate and possible? Well, initially, we might not know which are the important processes because this is to understand completely. So we want to offer parameters that might be correlated with these underlying processes. And the idea is that we're going to allow artificial intelligence to select the most important parameters, list of parameters that we offer. Okay, so now we are ready to apply AI. So as I mentioned, all of this AI analysis will be to map the performance as a function of only key important parameters out of all of the parameters that we offer initially. So these key parameters, in analogy to biology and medicine, we might refer to them as materials genes. And why do we use this analogy? Well, genes in biology, they correlate with some characteristics, for instance, color of the hair or color of the eyes, without, however, comprehensive information on how the DNA code transfers to this property, because it's way too complicated. So this is the concept that we also want to apply to materials. Also here we have very complicated materials functions. So this is the first reason we use this analogy. The second reason is that we are using here a statistical description. So as genes in biology, we cannot for sure, based on the genes, if a material will be a good or a bad catalyst, but we have a statistical description, so we have some uncertainty related to this prediction. So that's the second reason why we use materials genes. And some people also talk about materials genome as this, all of this combination of these genes. Yeah? So that's kind of the key concept here. Switching from atomistic modeling, where we try to comprehensively describe everything, to this more correlation-based analysis, where we don't rely on a physical model. Okay, so in other words, what you find here are coordinates of such maps of materials that I will call descriptor. That depends on few of these parameters. We don't want coordinates that depends on a lot of parameters because the interpretation of the model more difficult. So we want like only few parameters there. Okay, so for this to work, so finally, if we are successful in this, we are going to have predictions because we have a model, but we also hope to get some insights because we have selected the most important parameters that correlate with the underlying processes. So we hope to say some of the processes that are the most important. Okay, for this to work, we need these AI methods to at least have do two different things. First, they need to so they have to be able to handle the amount of data that we have from experiment. And as you can imagine, these systematic experiments, they don't today with the tool. It's hard to get a large number of materials using this type of systematic data where we really characterize all the materials. So these AI methods, they have to handle that. And first, if you want your selection or identification of these key parameters, the AI methods, they need to be interpretable. And in this presentation, I will show you like two of these methods that can have these requirements. So the first one is regression and the second one is subgroup discovery. Okay, I will illustrate this with two different applications. So I start with the first application. So here we are going to be looking at materials that are cobalt nanoparticles supported on an oxide. It's a silica oxide, which was modified by these M elements. So we introduce elements in the silica support by keeping the cobalt nanoparticle, and we form these systems here. And these are applied in a reaction that is the CO2 hydrogenation to methanol. So why do we systems? Actually, our experimental collaborators are looking at these systems because they mimic the environment of hydrothermal vents. Yeah, I don't know if you guys have any idea of what that is. Thermal vents are fissures on the seafloor that discharge heated water. And people have been looking at these systems because it is believed that the first organic molecules in the planet Earth were type of systems because we have hydrogen, we have CO2 at the time, and we have also minerals here that can catalyze this reaction. So that's why people study this type of systems. Here is the system, and what is interesting about the system is that here I show the selectivity and CO2 conversion for different metals that are introduced in the supports, minerals that we have in the seafloor. So depending on the metal that we have in the support, we have a different reactivity, so we form different products. So this is interesting because it means that the support has the products that we're going to be forming. So here you see that this is titanium, zirconium, aluminum, calcium, magnesium. Okay, so what are the questions here? So we want to understand what is the role of this. So why changing this metal affects the reactivity, and from the perspective of climate change, we would like to develop new supports and maybe we have that can transform CO2 into something useful. Okay, so this is what we have done. We have created an experimental theoretical data set using this approach that I discussed before. The measure performance, which for us is going to be the methanol selectivity. So this reflects how much of the products are methanol, which is what we care about. So we don't want to form methane or CO. We are interested in methanol. So here we have extremely small number of data points. So 24 data points. We have 6 materials that have been measured under 4 different conditions. So this is our target in the analysis. Now, discuss also these candidate descriptive parameters and where they come from. So we have 33 of them. So we have parameters that come from the experimental characterization of these materials. So here you see all were used for creating these parameters. So here we have microscopy, we have temperature program reduction, we have electron microscopy, and so on. You see here there is a range of different techniques that ways in detail these materials. Then we have theoretical parameters that will come from a DFT calculation. So here we are using DFT GGA calculations that were performed code. And here I show you a bit more details on these parameters. So we created the system here. So it's I think you cannot see very well, but it's a cobalt 50 cluster that is supported in a more. So you see here, this system is much more simple than the real system. We have only 50 atoms of cobalt. This is much smaller than the real system. However, we hope to find correlations between parameters that were calculated the experimental reactivity. So what enters here, for instance, the CO2 absorption energy, the CO bond elongation of adsorbed CO2, which reflects the activation of this molecule. And so here you see that there is a bunch of different species that were adsorbed in this model system and for which we calculate the formation energy or adsorption energy. So they are all offered. We don't need to choose the action. We just calculate possible mechanisms and offer them in the analysis. Okay, so then finally we have elemental parameters that are very simple properties of the elements that enter in this material, in the support. For instance, electronegativity or covalent radius. So these are experiment or calculation. Okay, now we are ready to apply AI. We are going to apply a method that is called Shor-Independent Screening and Specifying Operator, in short SISO, that has been developed by my colleagues at the Fritz Haber Institute a couple of years ago. So this is an approach, and what symbolic regression does is to find analytical equations that describe data. So if you think about linear regression, we have like a fixed form, and we fit if here we are going to fit at the same time find the functional form of the model and the coefficients. We do this simultaneously, and this is what it's called symbolic regression. Different flavors to do that. I believe this is one of the best we have today, the SISO, so that's why we are working with that. And I show you how this works. So the first step of this approach is the choice of input. In the context of SISO, we call primary features. So this is a very important step, because if we miss the important parameters initially, we will not be successful in finding a model that is useful. These are the primary features for AI. And then we have a step that we call feature construction. And we are going to combine these primary features according to unary and binary mathematical operators. And we are going to form a large candidate feature space that contains these analytical expressions. So here I would like you to note that we start from these primary features and we combine them in nonlinear ways. For instance, using exponential or powers or absolute differences and so on. So this is how we introduce our nonlinearity and complexity of the system in the approach. And we do this iteratively, so Q times, and this is what we call the rung. And you will see in the tutorial that this is an important parameter because this is a hyperparameter of the SISO model. So to select how many times we are going to apply these operators. Okay, so from the primary features we formed very different expressions, very nonlinear. And then what SISO will do is to a technique called compress sensing to select the few of these expressions that combined by fitted coefficients will best correlate to the target of interest, our property of interest. Okay, so how does this work? So there, two steps in this compressed sensing approach. So the first one we look at so this is the shared independent screening step, where we look at the correlation between these expressions. And then we select the most correlated features. These ones here, we have a subspace of this feature, and we actually scale to match the property of interest. And then we do the same thing with the residuals of the previously identified model. Yeah, so we do this iteratively, and we form this type of model. So here you see that this looks very linear. However, don't forget that this di here, these analytical expressions of what we call descriptor vector, these nonlinearities that we introduced in the beginning of the analysis. Yeah. Okay, so we are going to see more details like how this works in the tutorial, hopefully. I just wanted to mention here that also this dimension descriptor, so the amount of analytical expressions that we have there is also a hyperparameter of the model. Yeah. Okay, final thing I want to say here is that I told you we form analytical expressions. So for you to have an idea, we are talking about billions or even trillions of expressions. So this is the order of magnitude we're talking about. So we can think about these features as like correlating to different processes that are controlling our property. So we can think about a list of hypotheses of mechanisms that can be ruling this properly. Yeah? And here at the end, we are going to identify very low dimensionality descriptors. And here I'm talking about 2 or 3 descriptor components. So this D here, very low. Yeah? So it's not going to be a very high dimensionality. And this is how we're going to select features, because if we select only few of the expressions, only few parameters will appear there. Okay, good. And also here I note that we have very few fitted coefficients. So if you compare to something like kernel ridge regression, where we have 1 fitted coefficient per data point, here we have a very small. So we can have a data set that contains, I don't know, hundreds or 200s of materials, and we can have models that will have 3 or 4 fitted coefficients. Yeah? So that's how we prevent also models are overfitting. Yeah? For sure, we are going to do cross-validation to check these parameters, and I will discuss this a bit later to make sure that we are not having a too complex model. Yeah, but this is the overall approach. Okay, I discussed how this works, so let's jump now to the results, and I show you how this can work and the usefulness of the experiment. Yes, please.
You have this enormous space. How do you explore the space? You do simulated annealing or random search? What do you do? I mean, you have a function at the end with L0 or whatever regularization, but how do you explore these things that is very...
So it's this, what we are doing here is L0, yes, but we cannot do L0 in a billion of features because this is combinatorially a problem. So the way CISO is solving that is by first, so we are selecting such huge space in which we do L0. And that's the usefulness of this CIS approach, because we are just taking these hundreds or thousands of features that are the most correlated with the property individual, and then we apply L0 in this reduced space. So the L0, so we might have here trillions of features, and we might only do the L0 in hundreds or of candidates. Does this answer the question?
Yeah. I was just wondering if it is a Monte Carlo or it's not
so this is a deterministic method, and we are doing this construction of these features in an exhaustive way. And we check the correlations between all. This is cheap, yeah. This is a linear, so Pearson correlation. And then we reduce the space and the L0 there, yeah. So there is nothing, so another approach is based on genetic algorithms. And there you have this type of, you evolve this, you evolve the expressions from different generations by using random perturbations. This is not the case here. And it's different from the genetic algorithm approach. Any other questions actually now? Yes, please.
Thanks a lot. I'm curious, at the end of it, are there expressions that have any kind of meaning, like you can actually look at it and see that it's compact enough to interpret as a human? Because every time I've tried symbolic regression, it gave me a whole mess. So basically, I already needed to know the answer to make any sense of it, so I would have been better off using a black box model anyway.
Well, what people have shown is that if you have a closed expression for the model, for the property you're interested, based on the features, you can find it. However, you can find this expression and we will have a physical meaning. However, in our cases, with catalysis, we don't even know if we can write a closed form to describe a property. So in that case, we have to be aware that this is a correlation. The expression itself will not have a physical. The parameters that enter there, they do have a physical meaning, and they often reflect the previous knowledge of the systems. So we have some confidence that we can obtain that from there. Yes.
Thanks. I have a question about the linearity, non-linearity. I understand in the final expression that, of course, there you can have functions that are highly non-linear, whatever you want. However, in the previous step, so when you do the actual compression, then you discard redundant features based on a linear correlation. Is that a point that you might want to improve by, I don't know, introducing something like mutual information, or because the last step is going to fix it anyway?
Yeah, it's definitely a good point. So I would claim that when you have these residuals here, you will capture whatever you missed in the screening. And we could imagine using mutual information for this independent screening, but then you cannot handle like large feature spaces because it's going to be expensive. It's definitely a way, but I think it will make it more computational inefficient. Any other questions for the moment? I'm walking around the room. Okay, so hopefully this is going to be clear when we discuss the results. So I go now to some of the results. So we go back to the CO2 hydrogenation business now. And here I would like to discuss this that reflect, so I don't know if you're familiar with these plots. So we have box plots and violin plots. So the width of this violin reflect the number of systems with a certain, so we are looking at prediction errors, and we are constructing these violins to reflect the distribution of prediction errors. Yeah. Okay, so, and we are doing this for different types in order to assess the performance of the model. So here, if we use only the theoretical features that are coming from the atomistic simulation, this is the distribution of error. So we have really high error sometimes. So there's something that the theoretical model is not capturing, actually. So there's something missing. Now, when we combine theoretical and experimental data, we have a better fit of the model. And when we combine the three types of parameters, we got even better. So this shows that there is a synergy when we use experimental information together with theoretical information to model always the experimental target. That our target is always coming from the real experiment. Okay, so this we are happy because this shows that yeah, there is some usefulness in combining experimental with theoretical. And now we can look at the model that we obtain with this combination of features, and hopefully this answers the question there. So this is the model for the selectivity. And it's a rather simple model, I would have to say. So, and here we see the parameters that enter in this model, and we can use these parameters to try to understand what's happening. So first here we have the conversion, which reflects the degree to which we converted the initial molecule. And then we have parameters that come from, so elemental parameters, so the covalent radius of this element that we introduce into the support. About the structure of the support that is important for selectivity. We have the formation energy of the methoxy of this species here on the surface that was calculated by the atomistic model. Is that there is something about this intermediate that is important for reactivity. However, we cannot tell exactly if this intermediate is in the pathway, the reaction pathway to form methanol, or maybe it's blocked. This we can further investigate based on this model, but it's something that is correlated. And finally, here we have an experimental parameter that reflects the reducibility of the material and its impact for. And here, this is the temperature of the first temperature program reduction signal. So you see here, so this is the consumed hydrogen as a function of temperature, and for the different materials, they're reducing at different temperatures. And it seems that this first reduction temperature is a parameter that is correlated with the reactivity. So this is the type of analysis we can do to extract some chemical or physical models that we obtain with CISO. Okay, so now what we can also do is to create these maps of materials. So here I'm plotting the conversion and this part on the y-axis, and this color reflects the selectivity towards methanol. So we want high selectivity, so here this tells us that we have to go in this area of the map. So here's that were used to train the model, and here we can hopefully use this map to design better materials or to modify an existing material to improve the performance. Yeah. So this is also what CISO provides. Okay, so finally we also have trained the model only based on the elemental features. The performance is not as good as this one, but it's actually surprisingly good. Parameters. And the advantage of this model is that we don't need to use any experiment or calculation to evaluate or make a prediction, because these parameters that enter in the model are very simple. So we have used this model in order to make predictions to the whole periodic table. So here you have the atomic number and the predicted selectivity of methanol that we would produce different elements in this silica support. And you see there are different reactivities and different trends. We have selected 2 of these materials that had the synthesis methods reported in the literature. We have made it, so our collaborators have made these materials. And here we look at the predictions that we have. So for instance, this vanadium-based material has this predicted selectivity quite high, and material has this selectivity. And we also want to evaluate how much we trust this prediction. So we have created ensembles of different models in order to evaluation of these predictions. And here we are using models trained with 1 left out material because we have an extremely small data set. And here we see that from this prediction, we expect that the prediction for the zinc material is worse than the prediction for the vanadium-based material. And so these are the experimental results, which confirm what we have seen here. So of course, so here 32% and 16% in this case. So we have a disagreement that is higher for this zinc case. Of course, this is very like a small number of materials. Yeah, but this gives us some confidence that the CISO model can be used for predictions and also for to understand the reliability of these predictions. Okay, very good. So this is a presentation. I'm running out of time, but I would like to discuss now the second application and a second issue that we have in material science. So the models that I showed you before and other publications we had with this approach before are taking the whole material space and training a model. We take the whole data set and we fit a model. And here I would like to question to be done. And why would it be like a bad idea? So first, if in general, when you have a data set in material science, we know a lot of materials that perform poorly, materials that are good ones. I mean, if we knew very good materials, we wouldn't have a job here, no? So we often have a lot of, so if this is the performance and this is some type of descriptor, we often have a lot of data, but not a lot of data points here. Yeah. So there is the risk that by fitting to the entire data set, our loss function is prioritizing this region here, the description in this region here, and not here. This is the first reason. The second reason is that we might have in a material space very different mechanisms governing the property we are looking at. So does it really make sense to fit one entire material space? Okay, so what I would like to discuss here is like a way of having a focus model that will not be fitted in the entire data set, but we are first gonna have this data set where we should fit the model. Yeah? So this is what we call a focused AI approach. And this will provide us a local model. This approach, as I mentioned, will first identify interesting subsets of data. And then once we have done that, we can fit a model, regression model only in this subset. Group discovery and CISO later. Okay, so a few words about this method that we're going to use now, second method of this presentation. It's called subgroup discovery, and the goal of this method is going to be to describing outstanding data points. So what does it mean? Let me walk you through the 3 steps of this method. So here is a description of what the method is doing. So given a population P tilde of a population P and a target Y that we are interested in, we want to identify descriptions of subgroups of subsets of the data set that are statistically most interesting. Okay, it's a bit of a long sentence, so let's go through the steps. So we need 3 elements here. First, we need a description language, which is going to be how to describe these different subsets set, we need an objective or quality function that we're going to optimize to find the subgroups. And then we need a search algorithm. Yeah? Okay, so first for the description language, we start with a data set that has interest and these candidate descriptive parameters or features. So what subgroup discovery will start doing is to create propositions about the data that are, for instance, inequality that restrain the value parameters to certain thresholds. For instance, this feature has to be higher than a certain value, and then the other value, this other feature has to be higher than a certain value. So we create a lot of them by using this. We create a grid in our feature space. This is the first step. Second, we need to define what is a group, or what is this statistically most interesting. And this will be encoded in the so-called quality function. So this is a function that describes the quality of the group. And the first term here is what we call the coverage. So this is the ratio between the size of the subgroup and the size of the data set. So this reflects the relative size or the number of data points in subgroup compared to the number of data points in the data set. So this term, this prevents the identification of very small subgroups that are not relevant. We want to have a group behavior when we use subgroup discovery, not a single point. And then the second term here is what we call the utility function. And here we are going to tell subgroup discovery what is interesting for a certain application. So one example of a utility function that we have is what we call standard deviation reduction. And here we have the standard deviation of the property in the data set minus the standard deviation of the property in the subgroup. So if we try to maximize this, we are going to find subsets of data that have very narrow distributions of the target of interest, our for instance, catalytic performance or anything you want. So this is an example of such utility function. So, and then when we have the description and the objective, then we need a search algorithm. So here we are going to use an algorithm called opportunistic pruning. So here we have a Monte Carlo type of approach, where we are going to create conjunctions of these propositions. So we combine these propositions so that we maximize this objective function. So we find such descriptions like this, and this is an example of distribution of this property that we might have if we use the standard deviation reduction utility function. So at the end of the analysis, we are going to have identified key parameters out of all of these offered parameters. So we also have feature selection here. And we are going to identify these rules that are these inequalities that describe the behavior of this subgroup. So this is also interpretable. Okay, any questions so far for the subgroup discovery? I know this was a bit fast, but I hope that with the application this is clearer. But please, any questions we can discuss now. Okay. So now to recap what we're going to do here. So it's also an application in catalysis. So we want that a catalytic material first is active, so it converts our reactant. But we also want that this conversion is toward a certain product. So we want a selective catalyst. So in this first step, we are going to identify descriptions of materials with noticeable activity using subgroup discovery. And then in the second step, we are going to fit a CISO model that is focused on situations with noticeable activity. So this is why this is not a global model. We're going to fit CISO only to this subset that is identified in the first step. So here you can think about other properties that could be modeled like this. For instance, if you're interested in electronic properties, for instance, band gaps, but we also care about the formation energy of the material. We want the material to be stable and synthesizable. So we can think also of this first property to be formation energy, and we find descriptions of materials with low formation energy, and only for those we fit a model for the band gap, yeah, if it makes sense for you. And I'm actually very happy to discuss other ideas you might have where this approach can be useful. So please let me know at the end of the presentation. Okay, so second application, so a few details on experiments here. So we team up with a different group now, and they are synthesizing materials using this mechanochemical approach, where we actually put powders of the precursors in a ball mill. Yeah, this is this equipment here. So we shake this thing with balls here and the powders, and we form the catalyst materials. So these are, again, supported nanoparticles. So we have metallic alloys here, and this support here is a high surface area alpha alumina material. So this is actually a very convenient way of making materials because we have high atom efficiency, so we don't have solvents and all of these things that we need for wet synthesis methods. And we have improved materials. For instance, it has been shown that the materials formed with this approach, they can have, for instance, high surface area. In applications like catalysis, this is crucial because it's a surface phenomenon, so we want to maximize that. Okay, so these are the 12 materials that we're going to be using. So these are palladium silver, palladium copper, palladium gold alloys, plus some pure metallic systems. And they are going to be applying this reaction. So this is the acetylene selective hydrogenation. So I don't go through the details why this reaction is important, but trust me that this is a very crucial reaction in the context of chemical energy conversion, because we can use a plasma process in order to convert methane to ethylene. However, and this plasma process can be run with the surplus of the energy of the grid. For instance, during the day, you have a lot of the sun, so you can use this surplus of energy to run this process. The problem is that we form ethylene, but also acetylene in this process. And then we have to convert this acetylene in equimolar streams with ethylene to ethylene. Yeah, so we want to convert acetylene to ethylene 100%, because this is more useful chemical, for instance, to make polyethylene or something like this. Okay, so here is we measure the acetylene conversion experimentally. So these are the reaction conditions. We have 1,000 data points. So this corresponds to these 12 materials measured at three different reaction temperatures and at different times, or times on stream. So we monitor the reactivity during the reaction time. And here we see, so this is the number of counts and the acetylene conversion. So this reflects how much of the acetylene we are converting. So we see some data points related to non-activity. So this, the catalyst is basically dead. There's nothing is happening. But for many situations, we have full conversion. So all of the acetylene is converted. So in this case, we have either 0 or 1. And we are interested in this case here. We are not interested here in these data points there. And then we also measure the ethylene selectivity. So this ranges from 1 to -1. And we are interested in selective materials that have this value positive. And what is interesting about this reaction is that the selectivity is changing significantly with time on stream. So here, this is the time on stream in minutes. And you see here that for some of the materials, they started with a selectivity value of -1. And after hours, this selectivity goes up. So why is it interesting? Well, under these conditions, so 10 bar of pressure, it's very difficult to do spectroscopy, at least in a meaningful way. And remember that acetylene is an explosive molecule, so this is very complicated to measure the material under the reaction conditions. And also, this time scale is hardly achieved by atomistic simulations, because it's a time scale of hours. So this means that we need different approaches to model this. Okay, so what we have done here, so we have selected 21 candidate descriptive parameters. So some of them reflect the reaction conditions, some reflect the properties of the entire material, for instance, the mean particle diameter or surface area, and some are properties of the elements that enter in the composition of the material. For instance, ionization potential, closest bulk interatomic distance, and so on. So these are, we have alloys here, so we take the composition average of these elemental parameters to create these features or candidate descriptive parameters. Here I'm also showing here the parameters that we got from theory. So here we have very simplified low index model surfaces where we calculate the parameters. So we have properties of the clean surface, but also properties that reflect the interaction of this surface with hydrogen and carbon, because we know that under these conditions we have acetylene and these molecules can interact with the surface, forming, for instance, surface hydride or surface carbides. That's why we offer this in the analysis. Okay, so now quickly to the results. I checked the time, yeah. So here, so this is the plot I showed before, and this, we apply subgroup discovery, and we find this subgroup here that is represented by this red color. So we were able to, by using subgroup discovery, to identify a subset of data that corresponds only to the high conversion, which is what we are interested on here. And so we have selected these data points, but we also have the description of this subgroup, so which tells us something about what makes an active catalyst. And here, this is the description we have. So the oven temperature has to be above a certain threshold. the closest bulk interatomic distance of the material, so this is the composition average, has to be above a certain value. And the binding energy of subsurface carbon has to be also above a certain threshold. So this is the type of description. What can we learn from this? Well, first, this temperature here tells us that there is a minimum temperature for the reaction to start. So this can be associated to the material solid state reactions that require certain energy to take place, or to the catalytic reaction. Yeah? Here also, this tells us that the interaction of the surface of the material with carbon is crucial for the reactivity. So this is the type of analysis that we can make. So for instance, we can be forming surface carbides that will hydrogenate this molecule of the acetylene molecule. Yeah. So this is the type of description we have with subgroup discovery. Okay, now a few words about the CISO model. So we model this time-dependent selectivity here. And this is the fit of the best model that we identified by CISO. So you see that this, well, it's not perfect, but we have like the correctly described, this model correctly describes the trend. And here again, I'm not going to go through the details of this, but we can look at the parameters that enter there. I just wanted to mention to you here that we have this exponential term that depends on the time. So this term depends on the time. So we are really able to use the exponential function to model the time-dependent selectivity or the time-dependent property. And this is, we can also fit bias terms here, as you see from this expression. Yeah, so there's if you're interested in the meaning of that, we can discuss later. Maybe it's not so interesting for everyone. So yeah, but we can do this analysis of the genes also here. Okay, finally, the last thing I want to show. So we have properties that are measured and properties that are calculated. So if we make some assumption on the measured properties, we can make some predictions because we can calculate these things here with DFT. So that's what we have done. So here we are exploiting this AI model to design new materials. So these are bimetallic systems. So we have created hypothetical compositions containing different metals under different compositions. And this in color here, you see the predicted selectivity to ethylene. So we want to have to be in this yellow area here. So we see that ruthenium is a promising candidate at this composition, and also silver, which we had in the training set, are also predicted to be good catalysts. We can do this also for trimetallic systems. So we have tested like this palladium, silver, copper, and here one can also identify promising compositions that can be tested experimentally. So it seems that it's very difficult to synthesize this material, this ruthenium one. So our collaborators are still working on that using the ball milling approach. But they have synthesized other materials, for instance, the palladium silver, that are more diluted than what we have in training set, and this trimetallic system here. And here I'm showing you the selectivity as a function of time for the measured value, so this blue one, and the value predicted by CISO. Here we see that we have some disagreement between the predictions and the model, but in general, the trends are correctly captured by the model. Especially think that this selectivity can go from 1 to -1. So the model is correctly capturing this selectivity. And also here we have at a long time, so we have some disagreement here, but at long time on stream, we can predict quite well actually the selectivity. So this, again, very few materials, but this gives us some confidence that this type of approach will be useful, especially when we can have a higher number of materials or high throughput. Okay, I don't have time for this part here, but I would just like to advertise that we are using now symbolic regression and CISO. We brought it to an active learning workflow by creating ensembles of CISO models to get uncertainty estimates. So I will skip this slide, but we have an application here where we are using this machinery in order to find oxides that are resistant under the conditions of the oxygen evolution reaction. So we are using Purba decomposition energy as a target in our analysis, and we are here calculating this with DFT HSE. So this is the approach that we use to calculate. So this is a very efficient method that is implemented now in FHIM's code. And in this paper here, you have the description of recent developments in the code. So I invite you to read, actually, if you're interested in this type of code, which is all electron for potential code. Yeah, and this is like a publication where we have details of that. And please ask me if you'd like to have more details. So this connects a bit with the presentation of Milica yesterday. So that's what we are doing here with CISO. Okay, so to conclude, here in this presentation I show like this material genes concept and how we can integrate this concept by using experimental and theoretical data. And I think the main point here is that we want predictions, but we also want insights. And this type of approach can give us predictions that are quite good because we are modeling the experimental variable or property. And we also have feature selection, so we can have some insights, even though we are not aiming at a full description of the process. So then here these two different methods that can do this data efficiently and in an interpretable way. This focused AI approach, I'm particularly excited about that because this is an approach that can handle different mechanisms that might exist, and I think they are existing catalysts, but also in other types of properties. And we have also the issue of unbalanced data sets that this focused approach will try to tackle. So I think it's promising, and please let me know what you think about it, and if you have maybe questions or problems where you think this can be useful, I would be very interested to discuss. Okay, so now I would like to acknowledge I'm not an experimentalist, so we worked people from, in this case, all of this work was done in Mülheim, in the Max Planck Institute for Coal Research, or Kohlenforschung. So these are the people that did the work. And here, this is my group in Berlin. So Matthias Schäffler, I would like to acknowledge for his support over the years. And this is my group. So this Ray is the postdoc that did the work on the CO2 hydrogenation. And Hersain was working with the subgroup discovery approach. Now he has a job in a company. And this is the different people in the group that are working with uncertainty quantification and active learning workflows. Okay, thank you all for your attention. I'll be very happy to take your questions now or later, as you prefer.
Any question?
Thank you very much for the very interesting talk. I have a question about the robustness of the model. If you change, for instance, either, so if you have uncertainty, both, let's assume you have uncertainty on the measurements. And do you expect that the functional form that is predicted changes most in the few D coefficients that you have, or that you have a change also in the functions that you plug in? Because you were referring, for instance, before at an, to an exponential behavior, and maybe if you just modify a bit the values of the data, you may have another behavior.
Yeah, definitely. This is a very important point, and they will change. So can you hear me? I don't know. I'm not sure. Is it fine? Yeah. So they will. The descriptors and the coefficients will both change. What we are doing now is that, so when we have a CISO expression, not all of the parameters have the same importance. Some parameters might be more important than others. So what we are working currently is to have a feature importance analysis on this, and then we can know like which are the measurements that need to be prioritized with respect to the error. But I don't know if I can give you an answer now, like how these descriptors change. You can, of course, look at the list of descriptors or models, and you see what are the different expressions that you get if you have noise. But this approach, so the reason I insisted on the systematic experiments and standardized experiments is that if we have so little data sets in terms of the materials number, this will only work if we have very good data and diverse data. So we have to make sure that we have standard deviation of these parameters as small as possible, which is very challenging for experimental works. Sometimes it's even challenging to calculate them for some of the experiments. I hope this can answer the question more or less. Thank you.
Hi, I have actually two questions, but the second one maybe later. And the first one is more like philosophical, I would say. Do you think in the future, in a few years maybe, we can just reduce to elemental and synthesis experiment conditions as input? Since elements itself will respond to the conditions and somehow to go to the input that will just capture everything with some amount of data or something.
It's a very good point. We have been thinking about that also. I think the difficulty I see here is that if we would ideally like to only have the synthesis parameters as an input for the model, right? However, the relationships that we would be searching for, if we start with the synthesis parameters, to map to the reactivity, this is a very large complexity gap. And we can achieve that with these methods, but we need more data. So that's why having properties of the material after the synthesis is helpful here, because this reduces the complexity of the relationship we are searching for. And one of the struggles of symbolic regression is the explosion of the number of expressions that you have when you offer more parameters or when you perform this more and more complex operator application to find analytic expressions. So I think in the future what we want to do is to couple this approach with autonomous labs or with high throughput experimentation approaches that are very useful. But at the end of the day, if we don't have any information on the structure of the material, I think it would be also very hard to get any insights. So I think maybe what we have is something in between is what would be ideal for the future.
Either Katrina, you want a second or?
I was thinking about the application you mentioned, maybe topological catalysts. So what do you think would be the right approach? Do we want good activity and then search if topological is important there, or the other way around? Focus on topological and then...
Yeah, here we are looking for high activity and then to the selectivity, right? But depending on the type of reaction we are looking at, an intermediate value of activity could also be interesting, right? So this approach, what it doesn't do is like this multi-objective type of approach where you want to find a compromise, because we are focusing on high activity first and then we model the selectivity. So in some applications, this might not work. And for that, I think the idea is that we have used these models, so especially the workflows active learning, to construct iteratively Pareto fronts where we have objectives that need to be balanced. And then you can have activity in one axis and selectivity in another axis. And that would be probably more efficient in general. Yeah.
Thanks.
Any other question before the tutorial? Seems not.
Okay, so now we move to the tutorial. So this tutorial here is going to be introducing reproducing the results of this publication that is here. It's like a very recent publication. It's under review now. The way I would like to do this is first highlight the main points that the tutorial that are important for the tutorial. Then I would like to show you. So and here we are going to be. We'll be running subgroup discovery, but not CISO. I'm giving the output files of CISO that we're going to analyze. And then finally, I will show you a different notebook and a different type of resources at the Nomad AI Toolkit webpage, where you can look at the details on how we can train CISO model from a notebook. Okay, so one of the important. So here you have some time. So can you all access the notebook? Please let us know if there's any issue there. Yeah. Okay. I'm using here a local version, but it should be exactly the same for you. Okay, so I think the main point I want to stress here for the subgroup discovery part is the fact that we have crucial choices there. And for the first crucial choice is, of course, the features that we use in the analysis. So if we offer features that have no correlation with our target, we are going to be lost. So, and the second crucial point is that we need to encode in this utility function here what we expect from the distribution of the target, what is interesting for our problem. So here we are going to be using for the utility function, we are going to be first using the standard deviation reduction, but I will show you we are going to be looking at how the results change if we change this quality function. Okay, so if you go down here, so we have some information about CISO. We're going to come to that, and here what I just described. So first we import everything, the data set that you can look at here. So here we have 3 different performance targets in this study. So we're going to be focusing on the acetylene conversion, this X acetylene for the subgroup discovery. And here I'm showing you just an overview of the targets. So this is not very important. Okay, now the parameters here, since this the main point of this presentation was integration of theoretical and experimental data. Here you can look at all of the parameters that we're offering this analysis. So you see here some of them, we have 12 materials. So these distributions of the values of parameters are quite short. We are looking at the distribution of the values of features in the data set. So we have here the experimental ones in the first line, and the remaining ones are from theory. And here, this is what I want to discuss with you. First, before we do any analysis, it's always a good idea to look at the data. And here I'm plotting the correlation between the Pearson correlation between all of the parameters that we refer in the analysis. And you see here that some of these parameters are very correlated with each other. So the correlation is quite high. I would like to highlight that for the CISO analysis, this is, or the subgroup discovery analysis, this is not an issue, because in the end we are going to have like a very sparse solution. So we don't have, for instance, this would be very problematic if we used L2 regularization or L1 regularization. However, we have L0 here, so we are going to really select very few expressions in CISO. And also, if you look at the subgroup discovery, we also have very few propositions that enter in these descriptions. So it's not a problem that we have correlated features. And actually, we, from our research, we see that sometimes differences between correlated features are important to describe a property, and they would be missed if we excluded the correlated features in the beginning of the analysis. Yeah. However, as a result of the correlated features, we might have models that depend on different features at the end. So we have to be mindful of that. Okay. So here for the subgroup discovery part, so this we're going to be using a code that is a Java code. It's coming from RioKD. So there are many different subgroup discovery codes in the market. This is only one option. So I encourage you to have a look if you're interested. I can give you also other suggestions. And so we are going to write the input file of subgroup discovery by using this function here. And here there's like a very important choices that we have to make. For instance, the number cutoffs here. So this is the number of cutoffs that we're going to be using to create these propositions about the data. So these inequalities. So here, this is done via k-means clustering, and we need to choose the number of propositions. So the k in k-means clustering. So this is an important parameter here. And here, this is the algorithms that we have here are also very important because that's how we specify the utility function. So this is like the pure subgroup discovery where we have the standard deviation reduction as utility function and the exceptional subgroup discovery where we are going to have the other types of utility functions that I will tell you about in some minutes. Okay, this here. Yeah, so in the beginning we are going to be using this utility function that I mentioned before, and it's the same one we are using in the paper. So here, what this does is we search for subgroups that have very narrow distributions of a certain target, in our case, the conversion. So you will see here, so here we're going to be looking at the results of the publication. So you can uncomment this if you want to repeat the analysis. And here are some of the, you can, by looking at the results, we can look at the different subgroups that were identified. Of course, in the publication, in the presentation, I only list one of the subgroups, but we have different rules here that can be obtained. And here they are listed along with their coverage and utility function values. And here I would like to highlight, so you see here, these subgroups are actually equivalent. So they're exactly the same data points that they contain exactly the same data points, but the description is slightly different. And this is because of the correlated parameters that we have in the initially in the analysis. Okay, so here this is what I showed you in the beginning, in the presentation. So we search for subgroups that have narrow values of the distribution of the target. So we find this one that actually corresponds to this almost one values of activity or conversion. So this is what we wanted. But however, note that we have never requested that these values are high. We are only looking for a certain range of conversion of target or conversion. So this is what we have here. We can also visualize these rules in the coordinates of some of the parameters that enter there. So this is, for instance, this is the type of the closest interatomic distance and the subsurface carbon energy. And now, like here, this is what when we want to change the results and verify the effect of the utility function on the results. So now, instead of having the standard deviation reduction utility function, we are going to be trying two different utility functions: the positive mean shift. Yeah. So here we are looking at subgroups that have a mean value of the property that is shifted compared to the mean value in the whole data set. So by this utility function, we are asking for subgroups that have high values of a certain property, our target. Does it make sense for everyone? Yeah. And analogously, we can also have the negative mean shift utility function that will prioritize the selection of subgroups that have low values of a certain target. For instance, if you have an application, the one I mentioned before, where we have a formation energy as a proxy for stability or synthesizability, you might want to use this utility function here because you want very low values. Right? So here you can run this. It will take some minutes, and I will just show some of the results that you might have. So for the positive mean shift, you might have very similar results to the ones before. You have you want to find subgroups that are having high value of this conversion. However, for the negative mean shift, you will find something different probably. You'll find subgroups that are centered on this very low value of conversion. Yeah. So this is so I think the idea here is to show that the choice of utility function is crucial when using subgroup scope. Yeah. Any questions so far? Does it? Do you manage to get the results in the server? Okay, so I just go ahead and now like discuss the main points for CISO, and then at the, hopefully we have some minutes to that you can call me if there is some specific question. Well, before going to the CISO here, there's we can also use other types of utility functions, for instance, based on the Jensen-Shannon divergence between two different distributions. I think this is quite a powerful tool to find exceptions, because we are really looking at similar distributions. And in some cases, that might be very useful. For instance, when you have a massive amount of materials that are very low performance, because then you will really focus on exceptions. So yeah, this is interesting. Okay. Now, for the CISO part, the crucial point I think that I want to make in the tutorial is that we need to tune the parameters of the model. Here we have two hyperparameters in. Yes, please. So it's just it's just a symmetrized version of the Kullback library, and we are using the cumulative formulation of this divergence because of computation reasons, so for efficiency. But this is exactly like a KL divergence. You make sure that the choice of subgroup and dataset they will not change the value. Yeah. So it's you're really looking for distributions that are shifted towards each other, that have a different narrowness at the same time. Okay, so so I told you that CISO will create these analytical expressions, right? And so how complex should they be? You know, this is about the hyperparameter optimization in the context of CISO. So there are two different hyperparameters. First is the number of times that we are applying these operators, so this Q here, which we call rung, it's not written here, rung Q, and the model dimensionality D. Yeah? So to select the hyperparameters and also to perform the performance, to estimate the performance of the model, here what we are going to be doing is a nested, so-called nested cross-validation scheme. Yeah, maybe some of you have heard about that, but here we are going to be two different splits, and we have an outer loop and an inner loop. So we are going to be using this outer loop here to evaluate the performance of the model. So here we have tests, 5 different test sets. So these sets will never see the training data. So we are not going to be using it to select the hyperparameters. This is going to be done in the inner loop. So for each of these trained data sets, we are going to split another time, and we are going to be finding what I call validation sets. So these validation sets are going to be used for hyperparameter selection. Okay, so here we are going to be using this cell here to obtain the indices for the inner and outer loop. And here, so this function here will be writing the input for CISO. And what I wanted to show you is this here. So here for each of the 3 targets that we are going to be modeling, we are going to be looking at the cross-validation root mean square error. So this is validation error in this inner loop for 5 different folds. Yeah? And here you see that the results for Q equals 1 or 2 and dimensions to 5. So here we see that, so in the green, red curve here, these are the results that we obtain if we only apply the mathematical operators once to create these analytic functions. That's the performance we have. However, if we apply it twice, you see that the performance increases. Yeah? So this means that by making more complex expressions, we are improving the performance. And this is the validation performance. So the training performance will always improve if we make more and more complex expressions. For the validation error might decrease at some point because this is prediction. Are we in the same page? Okay, so this is the first observation. So it seems that rung 2 is the appropriate one compared to rung 1 for this specific data set. It's not always like this, so it's very important that we check that. Second, we look at how this error evolves with the dimensionality of the descriptor. And here we see that as we go higher in dimension, we have a lower error, validation error. At some points, for instance, in this fold here, we have a saturation of this error, and it can even go up slightly. So this means that there is a maximum complexity dimensionality that is ideal for this data set. Yeah? Does it make sense for everyone? Yeah, please tell me if this is not clear, because this is a very important point and how we choose this dimensionality of the descriptor. So in this case, for instance, you can we chose dimensionality 3 because you see that in some of the folds, this is where this error levels off. And it's of course different for different properties, so case by case. Okay, so this is like for hyperparameter selection optimization. So basically what we are doing here is a grid search, but we look at all the values of Q and all the values of dimensionality. One could go as high as they want with respect to dimensionality, but I would say that the idea of the CISO approach is that we have low dimensional models. So if you have 50 dimensions, then I think this is the purpose of the model, because you have so that's, yeah, we typically look at these values that go up to 5 or something. This is a question, what hyperparameters do. And then the second product of this nested cross-validation is the distribution of test errors. So this first split that we have, now we have selected the hyperparameters, then we have to make prediction. And here I would like to encourage you to use this
Test.
Yep. Better. Okay. We still have some time, and I would before we close, I mean, of course, you can always come to me like after the tutorial or anytime tomorrow or whatever, during dinner. Before we close this session for lunch, you're probably hungry. I would like to show you like here, so we are not training CISO models in this notebook, right? But I would like to point to different resources where we can do that. So first, at the end here, if you're interested in subgroup discovery, especially or CISO, at the end here, you're going to find a list of publications, each associated to a notebook. So I encourage you to also look at this, because you will find different examples of where subgroup discovery and CISO are going to be applied. This is the first thing. Second thing is like something called, so we have already several speakers, I think, mentioned the NOMAD database. So this is a very important resource for computational and now experimental data. That is from a German data infrastructure project. But we also have what we call a NOMAD AI toolkit. So here you can find tools that will explain different types of AI methods for materials. And if you go here, so you can use the data from the NOMAD database here, but also you can have these tutorials. So if you click here, you're going to go to this, land at this page, and here you see a list of tutorials that are discussing different topics. So I think there are many good tutorials here for different types of applications. So I encourage you to have a look, and please contact me or my colleagues if you have questions. But this is a very good starting point for a project in a method that you're not familiar with. And here I would like to show you like this one method here, so symbolic regression via compressed sensing, a tutorial. So here you can open the tutorial, so you have to log in. And here, this is the tutorial for symbolic regression via compressed sensing. So in here, I think I didn't introduce CISO in this way, but you can also see CISO as with respect to this L2, L1, and regularization approaches. So this is how the tutorial will do. And here, you're going to be using a CISO ++ code that's coming from here. Yeah. So this CISO++ code is a code that we are currently using. It has Python bindings, so it's very convenient. And you can find documentation quite detailed for this code. So please let me know if you're interested. I can direct you to all the documentation and what you need. So here you see that the tutorial will use an example in material science. So the difference between different crystal structures. So the entrance between two different structures, rock salt and rock blend. Zinc blend and rock salt. And here, you can have more details on how to run CISO from a Python interface. Yeah, so I don't go through the details of this, but here you also have section on the lasso method that is also a method for feature selection using L1 approximation. Yeah, so this is, so here is the result. So we are looking at descriptors. So the data point in terms of script. So here you can also see that some of these CISO maps can be used for classification. What I want to show is this here. Yeah. So what you do here is to create this feature space. So this is the input of the method. And here you just fit CISO using this function here. CISO. Yeah, so please have a look if you're interested. And I think not only this tutorial, but other tutorials there are interesting. To discover new methods, learn a bit about them. Okay, so we still have some minutes. So please ask me if you have some questions. We have 10 minutes. Could you run actually the subgroup discovery? It's slow. How long? Are you waiting since the beginning of the tutorial? Okay, yeah. Yeah. So I encourage you to play around, especially with the different utility functions, and you can also, use your own data, and this would be, I think it's a technique that is a bit overlooked in the material science community, which is powerful when we are dealing with unbalanced data sets or we want to find exceptions. Any questions or comments at this point? Everybody's hungry. Okay, if not, please approach me at any time today or tomorrow, and I thank you all for your attention. See you at lunch. Thank you.
Thanks, Lucas. Again.
So I believe we can start this afternoon session with Patricia Koenig, who is going to tell us about physics-based generative models, improved sampling in inverse materials design. The floor is yours.
Thank you for the introduction. Okay, so today's talk is meant as a tutorial kind of guide to show you on how to train such a generative model. And because we heard it now a few times, what inverse design is, I will make my introduction very briefly. So in general, it's a computational approach when we're looking for a material or a certain composition that exhibits a target property. And one very common workflow that we've also now seen throughout the week is science-driven machine learning. So we start with a scientific question about a system. Sometimes the system can be a vast chemical space, like an inverse design. Sometimes it can be a very distinct property that we want to know to analyze our process. And the first step, as everywhere, is that we then acquire data, be it from our databases, or sometimes we need to start from scratch, because the reality, I come from like a solid state battery modeling and interface group, means that you have very sparse data. With this data, you can train your model and then infer back and get either your target structure or you get insights on your chemical system. In the same notion, I want you to look at science-driven generative AI. What's generative AI? That's a model that learns a probability distribution that looks like your data space, but it's not. So when it draws samples from your data space, for example, through denoising, then you get a new sample that has not been your data set before, and you can kind of expand beyond the data set that you sampled before. I will show you this kind of sampling process for a very simple two-dimensional Kappa surface with iodide and hydroxide adsorbents. In the end, I will give a very brief outlook on a three-dimensional system where we do this for amorphous crystals. And if you think now this whole project is a bit overkill, what I'm showing, it's for the simplicity to show you where the problems are in my generative model, and then we use that later for these amorphous materials. So what I can say about the system is that independence of where the sorbets are on the Kappa surface, you get a different work function. This dataset has been computed in quantum espresso, and the work function is an electrochemical property that essentially changes with this position. And in the data set, when you look at it, so you sample that sorbets on the surface, you relax it, and then you can compute this. It's relatively sparse represented on the higher and lower ranges, but these are actually the ranges that are very interesting for electrocatalytic processes, for example, because when you have, for example, cyclovoltammogram, the most changes in the voltage electricity curve happen at these high and low areas. So what is happening there? So our sampling problem is this very specific system, and that also encompasses our training data. As always, when we have a model in which we feed data, we need to find a descriptor that can be read by the machine and that has the inherent physics that is displayed in our system. I will show you in a bit how I'm doing that, and then I will also show you how I'm monitoring the training process and screen the data to then go with a selected data set back to my scientific question and evaluate what is happening. Yeah, my model is implemented in PyTorch. So as you all know, generative models, there's by now a whole slew of methods out there. In this talk, I'm focusing on generative adversarial neural networks for the capability of directing the generative outputs with a so-called conditional GAN. What is a generative adversarial network, or GAN? So you take a Latin space, which is a lower dimensional probability distribution, and essentially the generator learns to map this lower dimensional distribution to your bigger space that looks like your data, but it's not. That's why it's coined as fake data. And then there's a second neural network, the so-called critic. It sees the fake and the real data and then evaluates the score on these batches. And with this, you compute the loss function of this, the so-called Earth-Mover's distance. Both networks train each other, and that's also the brilliant thing, but also the one that makes it unstable. So the generator learns a feature, and then the critic has to learn this too to keep up, and vice versa. So both of them feed each other, hence also the name adversarial, because these two networks are fighting with each other in the training loop. And because of this, if you do some wrong choices of hyperparameters or your descriptor is not appropriate, you get gradients that are not so smooth, and then this training process can get stuck in mode collapses. But I want to show you today how I'm kind of circumvent and navigate through this. So let's have a look at the descriptor space. As I said before, it's a two-dimensional surface system. What you see here is the double slab structure that comes from DFT for convergence reasons. But when you actually look at the below first kappa layer, there's not much happening. The positions of the atoms stay almost the same. It doesn't matter for that sorbets, so I chop it off. Then, okay, imagine you have a point in space that is three-dimensional, x, y, z. And for the simplicity of this tutorial, the z coordinate of my adsorbents and of the kappa is also, on average, mostly the same. So I only am concerned with a mapping to a two-dimensional grid, also because my neural network is a convolutional neural network, and with 2D layers, that is dirt cheap. I can train my network within 4 or 5 hours on an old A30. And yeah, so I use a grid assignment function from the particle mesh methods. This function has the advantage that the spatial cutoff is defined, so it is on all 4 grid points, and we have a weight conservation. And by choosing it this way, you have a certain sparsity in your data set defined by the background that is zeros. But when you choose the appropriate resolution in your grid, the training process is also more stable. So that's really a key point in my training itself. I apply this format mapping method. And as I said before, I'm actually interested in this enhanced structure property sampling. So my work function that I bind, I take the integer labels. The integer labels are more for me, for bookkeeping. The neural network itself sees an embedding layer of that. So it has a lookup table and can generate some flexibility with how close are the groups actually related to each other. So all of this goes into my model. And let's say I'm in the training loop and I think my training is relatively converged. What can I do? I can look at the in-image space, so I'm not having backmap to Cartesian coordinates. I just look at the quality of my images because we're here in 2D space. And one very simple metric that can be used for this is the structural similarity index. That's a filter from computer vision. And it's essentially a window function that goes across your image, and it can account for luminescence, brightness, edge detection. And with this score, this is an average value, so this is not really the distribution on the single batches, but for the simplicity of the slides, I just take the average because I want to qualitatively discuss this right now. So I compare the data set with a batch of generated structures, and I see that the SSIM is 1 if it's exactly the same image, and it's 0 if it has no features at all in common. So I see, okay, my data set and my generated structures already are fairly close to each other, but my generated structures, several batches of those, they are almost at 1. And that looks a bit dangerous to me because what I said in the beginning, the mode collapse means that the same features are learned and there is no diversity in this. But this is really just like a window function that goes over it and shows me the quality. And one difference between the data set and the generated structures is also the data set has the zeros in the background, and the generated structures always have this little bit of faint background noise. And I actually found that this adds up to this kind of similarity score. Another one is using the Earth mover's distance itself. That is a measure that says how far are the two probability spaces away from each other. And when I do this, this value would be theoretically 0 if you would really have perfectly exactly learned every feature and produce every weight the same way. Between the data set and the generated structures, this value is fairly low, and between the generated structures is even lower. Fair, they are again more similar to each other than the data set and the generated structure. But the cool thing here is it's not 0. It's also not so far away, so we don't have a mode collapse here because then this would be like really close to each other. And then something else that I need. The power of generative models is that once they are trained, they are fast at producing the data. If I now say my generator, oh, I want a structure with work function in the interval 0. How do I know it is a work function in the interval of 0, right? If I go back to DFT for each of these structures, ciao, cacao, then I didn't win anything. Then I just wasted a lot of time on GPUs. So for this is really where the interplay, I think, comes in hand between generative AI and machine learning interpotentials or regression tools at all. You need a cheap filter tool to then assess your data. So for this, I have a Gaussian process regression that essentially outputs the floats, and then I bin it back into my diagram. And what I can see here is the expected binning labels and the predicted ones. And on the main diagonal is the most, how do you say, so most of the bins are actually where I expect them. They are on the main diagonal. And the expected distribution and the predicted distribution for my data set are the same. So I can say within my descriptor space, after I mapped it back, that my GPR can be used as a cheap tool to say, okay, yeah, this structure should be in this work function interval, and no, this is not. And with this, I reach my suitable structures and can start my data analysis. Quick reminder again, I'm having my data set. I have the areas that are sparsely represented and which I'm very interested in. Depending on if it's a hollow or a bridge site, is also a very key factor in chemistry that it can determine the processes. So what I look now is at the statistics of how well did my generator learn these features in the higher and the lower ranges of my probability distribution. This is the data set. So this distribution that you see here is the hollow and bridge references in my data set by DFT for the hydroxide and the iodide ions. Comparing this gives me the possibility, A, to statistically look at what is my generator outputting, and if I then find anomalies, to check what is the motive that is recovered and how does it look as a play together. So if I just let it run, for bigger than 4.5 electron volts, I see that similar trends are reproduced. Of course, it will never be the same. That is actually a problem with generative models when you really want to statistically evaluate them against what your data set does. And then I let it run for the low ones, but what do we see here? There's no more iodine, right? So let's look at the motives in this range. What do I learn? And one technique is when you have generative models, you take one motive from your data set and then you let it generate until you have like a matrix that measures the similarity with one element and say, yeah, okay, this is actually very similar to what was in my data set, and how new does it look? So novelty and also sensibility for us, because we're looking at physical-chemical structures here. So one motive that, for example, then comes up is this. What do we have here? That's a bridge position. When I look at my data set, I don't have bridge positions for hydroxides, and it's actually where my GPR comes into play. It filters this structure really fast out. So this never enters my statistics, and this is why I never have a bridge in hydroxide. Then I keep going, and then I find, for example, this motive. You can see that the position of the adsorbents is a little bit of a periodic mapping. For us as humans, we can see this. This hydroxide has been mapped to the downside, but I also see that the kappa positions are a bit different. Later, when I will do this, for example, for amorphous crystals, it's actually really cool, because I have these atoms that move, so I actually do want some new structural gases to, for example, get to transition states. Now to our question, what happens with the iodine? And this can be a lesson for everyone. In the data set, in the sparse represented region, this structure is the only one that has iodine. That's one structure in my data set. So what you need to do when you have one feature that's actually crucial for the chemistry or the physics of your system, repeat that structure, augment it to the system, show the network that this is important, because I had it in this version that I'm showing here on the slides, only once in. And then what is happening is that, yes, I get iodines at some point, but the network never learned in this range for my latent space to do 8 at once. So it pops up sometimes very randomly, and of course that's energetically extremely unfavorable to be that close to an hydroxide, so it gets filtered out. So very quickly wrap up, I had my sampling question, training data goes into my model, I have cheap tools to evaluate my generation, and then I do data analysis. And here is another data set that is also sparsely represented. It's essentially created with a grand canonical Bayesian hopping method, and I see that especially in the stable structure energy groups, I have a lot of representation, and then the ones where it's lower for the catalytic conversion, which is actually the interesting part for our physics, it's very sparse represented. So I have the same mapping, I train my generator, I go backwards, and here my cheap tool to evaluate it is a gap, because we had it trained back then and we didn't change to like more modern methods yet, because it's more the generative model development on my side. And we are working there also on structure similarity indexes and matrices, but that's actually really hard, because an amorphous crystal is harder to trace than a 2D surface. So this, I want to thank you for your attention and my group and funding.
Questions?
Nobody?
Hi, just a quick one. Sorry, I missed it because I was thinking about a lot of things. The Earth mover's distance you're using to do what? What is it an Earth mover's distance of?
And beyond that, I also use it to compare between the data set and the generated structures to see, okay, am I getting in a mode collapse? How does it evolve? Is this a point now where I should stop the training, where I can stop the training? Because in the beginning of my training processes, when it wasn't so stable, I had, for example, really beautiful stripes that were continuously in my images, so I can capture that with this.
So let's thank Patricia again. And we have Oliver Loveday, who is presenting CARE, an end-to-end framework for reactivity in heterogeneous catalysis. The floor is yours.
Okay, can you switch mic? I would tell you. Okay. Are you staying there?
All right. So, thank you all. Today I'm going to talk about the work that we are developing at ICIQ in Tarragona under the supervision of Nuria Lopez. And basically, we are focused more on heterogeneous catalysis, but also in materials and so on. And basically, our question was that, okay, when you work in heterogeneous catalysis, basically, your problem is a certain reaction that you have to decipher the mechanism. So usually what we do is we propose a mechanism, you evaluate it with DFT, and typically we just draw the reaction profile. If the reaction profile, for example, matches experimental evidence, we will give it as valid. Otherwise, we will probably propose another mechanism, reevaluate it, and so on, until we find something that matches experimental evidence. The thing is that we have seen recently that, well, DFT takes a lot of time and a lot of computational resources, and in the last years, we have tried to bypass this using machine learning models, mainly machine learning potentials, which I've seen that, well, we have seen that year by year, we're improving and we kind of can bypass DFT. But our question was, okay, we are just bypassing DFT, but is there a way to like automate and improve the other two parts of our research? And this is our question. And our answer is that it's called CARE. And basically it's an end-to-end framework that it's consistent of 3 modules. That the first module will generate all the possible reaction mechanisms. Later we will evaluate them with machine learning potentials. And last but not least, we will also evaluate the microkinetic modeling, because we won't stay only in the thermodynamics, we will also want to study the microkinetics, because otherwise sometimes, well, a lot of processes are kinetically driven. So basically the first module is we generate the chemical reaction network blueprint, and yeah, basically what we do is we have developed an algorithm that through molecular and reaction templates, we just build all the possible intermediates and reactions in a process. The good thing about this algorithm is that you don't have to provide any sort of input structures or so on. You just provide your interest boundaries. So for example, if you wanted to study the metal decomposition into CO2 or CO, what you would do is you would define your network with 1 carbon atom and 2 oxygens, for example. So the good thing about our blueprint is that, well, since we want to do it as generalized as possible, species are available in, the species we generate are available in many different formats. So we work with ASC, RDKit, smiles, formulas, inches, and also graphs. Also, we have templates to work with thermal and electrochemical catalysis. So basically, we take into account PCT reactions and also pH and potential effects. And also, our blueprint, is catalyst agnostic. So as its name says, it's a blueprint. So you would have all the reactions more or less with these expressions, and you will choose your catalyst later. So once you build this blueprint, you can use it as many times as you want to study all of different processes. And also, yeah, you can choose, you will later be able to choose if you want to study like a single facet. Also, you want to treat your system as a whole nanoparticle. And a part of being catalyst agnostic, our chemical reaction network is undirected. So basically, you just choose, when you're doing the microkinetic modeling, you will choose where do you want to start and where do you want to finish if you want to know where you want to finish. Otherwise, you can just let the kinetics decide. So basically, once we have done the chemical reaction network blueprint, we have to evaluate it. But before evaluating, we have to choose surface or what nanoparticle we want to study. So basically, you can just choose whatever material you want. We have integrated the materials project API. Also, you can provide your own surface or slab, that we have an algorithm that will automatically readapt your slab to a surface. And also, we provide, just in any case, a database full of metals. So once you have chosen your surface, species are automatically placed on the surface. You can choose how many adsorption configurations you want. By integrating ACAP, DocOnSurf, and Graph Theory, what we do is generate as many possible configurations, as possible in order to reduce bias. So once we have placed the adsorbate on the surface, yeah, we evaluate it. Mainly, CARE works with our own developed network, which is GameNet-UQ. GameNet-UQ is not a machine learning atomic potential, it's an initial structure to relaxed energy. So just by providing an initial guess of an input, we just transform it into graph, pass it through GameNet, and we will just get an energy. It also has uncertainty quantification, so the model tells you how reliable, how sure it is of its own prediction. But we just don't stay here, since we know there are a lot of machine learning potentials developed nowadays. So we also provide, and with GameNet-UQ, you are able to study gas phase systems, intermediate adsorbed systems, and transition states. And mainly it was trained on these transition metal surfaces. So we were pretty ambitious, and we just don't want it to stay on GameNet. And what we did is also we implemented interfaces and functionalities for many state-of-the-art machine learning potentials. So currently we only have these models implemented, but we are trying to implement every day more and more models. And these are machine learning potentials, so if you want to like pre-optimize your configurations and evaluate them with these models, you can. As of right now, these models are used as out-of-the-box models, but if you also have your pre-trained models where you have did some fine-tuning and so on, you can also integrate them. And last but not least, the microkinetic module, which basically it's this link between atomistic modeling and experiments, and we have developed some, we have some functions in Python and Julia. And so basically with CARE, what you can do is automatically generate chemical reaction networks in a very fast way. You can also automatically place adsorbs on any surface and generate as many configurations as desired. You are able to evaluate a CRN both in CPU and GPU with whatever module you want. Also, you can treat your catalyst as a single surface or as a nanoparticle in electrochemical or thermal conditions. And you can also like benchmark your own model or different models. You have DFT data or experimental data. So to showcase CARE's capabilities, here there's a couple of case studies that we have selected. So the first is, for example, activity trends in ethanol decomposition. And for this case, what we did is we selected a C102 CRN, which basically contains 28 intermediates, 10 gas phase molecules, and 62 reactions. So we got this blueprint and we evaluated 63 times for all of these different metals, and basically generating, evaluating, and doing the microkinetics for all of these 63 chemical reaction networks took only 77 minutes. And with this, what we can do is, for example, we can study the different, as treating each facet as their own or treating it as a nanoparticle. So what we did is to convert from here to here is just do the weight contribution of each facet on the nanoparticle. So we would streamline our results. Other things that you can do is, for example, is benchmark your results with DFT data, if you have DFT data, also with experimental data. This is from an experimental database, which is called CAT-TEST Hub. But I think that at the moment, this experimental data is pretty scarce in order, if you want to benchmark in general computational with experimental. And another case study, for example, is that we can explore large chemical reaction networks that we were not able to study before, maybe previously with DFT and methodologies, classical methodologies. And in this case, what we propose to do is see if we could study the Fischer-Tropsch synthesis. And for this case, what we did is we built a C601 chemical reaction network, which had more or less 40K surface intermediates, more or less 1,000 gas phase molecules, and around 370,000 elementary reactions. So we evaluate this blueprint on 4 different metals, and just generating and evaluating all of these species took around 4 hours per CRN and on CPU. And basically what we can do is, in this case, is obtain trends that are comparable with experimental data, and overall you can just like study the thermodynamics and so on. And the conclusion is that, yeah, with Keru you are able to generate all of this chemical reaction network and like automatically study all of the process. You can use the model as the framework as a whole pipeline, or you can use like each model separately. So if you're just only interested in, for example, generating a lot of added configurations, you can just use that module, generate all of these species, and just like later evaluate them with whatever model you want or in the way you want. And basically as an outlook, yeah, we will try to expand to include new reactions and molecules in our networks. Also, since we're working with these models, we're just using like electronic energies. So we are not taking into account entropy effects. Also like like lateral interactions also not taken into account. So basically we are moving now towards direction to better depict reality. And yeah, overall we were just trying to improve each model. So I would like to acknowledge my team and the Financial Institution, and thank you all for your attention.
Questions?
Impressive work, Oliver. I was wondering whether you use the uncertainty in the microkinetic model to propagate the uncertainties from the absorption analysis into the final prediction.
Yeah, so basically, yeah, you can hear me, yeah? In the case study that I showed for the methanol decomposition, we didn't take into account propagation of the uncertainty, but our model includes that into the microkinetic modeling. So you could do like a couple number of runs of this microkinetic modeling in the span of uncertainty, and you would get this better depiction of the results.
I'll ask one more question, please. Did you try to compare some different DFT functionals? Because with this machinery, I think you now have access to the possibility of systematically comparing outcomes from different DFT functionals for the same reaction.
Different what, sorry?
DFT functionals.
DFT functionals. The thing is that we just implemented MLIPs or graph neural networks, so we haven't implemented like a module or a framework for DFT, but this could be used to compare performance of different functionals. you could just, for example, use the first module, you just generate all your species, generate all of the potential adsorbed configurations, and you would later the output into DFT with different functionals and just study.
Thank you very much.
Study this.
Yeah, how do you assess that your chemical reaction network really contains all the possible reactions? This is what you claim.
Yeah, that's a good question. Since there are a lot of possible reactions, what we did is, because this is just our first iteration of this model, so chemical reaction network completeness is pretty difficult to achieve. And right now what we did is mainly like in heterogeneous catalysis, most of the reactivity could be explained through bond-breaking reactions. So, but there are a lot of also like interface reactions and so on. So as of right now, we have include bond-breaking reactions. Also, we have rearrangement reactions and PCT reactions if you want to study electrochemistry. But we're missing a lot of reactions, to be honest. Sorry?
So why not include some algorithms for reaction path sampling then?
Yeah, that's also something that we want to move towards, because at the moment we only have these type of reactions, but if you want to like add more reactions, the problem will escalate exponentially. So we need some sort of algorithm to later check and explore these networks in a faster way. Because
I mean, but that's wanting to know the whole reaction network in advance, right?
Yeah, exactly.
Okay, so let's thank the speaker again. This is yours, or? You have your own. Thanks. I just introduce you. So here we have Alberto Perez de Alba Ortiz, who is to speak about novel Bayesian approaches to predict and design free energy landscapes. The floor is yours. I will tell you when it's 5 minutes left.
Yeah, thank you very much for the kind introduction, and well, of course, thank you very much to all the organizers for having all of us here. I would like to do the same as Luca in the morning and just risk it. I'm going to ask you to please raise your hand if you have ever done an enhanced sampling simulation or a free energy calculation. Good, so I see some hands coming up, you know, metadynamics, umbrella sampling, that kind of thing. Now, please raise your hand again, and I'm sure it's going to be way fewer people if your enhanced sampling simulations work from the first try. Absolutely no hands. Yes, so that's exactly what I expected. Cool. So what I'm going to show to you today is a few Bayesian approaches to try to, you know, have at least a few people raising their hands to the second question. And well, after showing you work, I'm going to show a couple of applications. One of them is about polymer rigidities, and the other about nanoplastic effect on protein function. So just to, you know, put us in context, when we talk about AI for molecules and materials, we're normally somewhere in this plane, where you can have either, you know, poor data regime or rich data regime in the horizontal axis, and in the same way you can have accessible experiments or very expensive experiments. By experiments I also mean, you know, digital ones or simulations, right? Now if you have a good situation for both, your problem is likely solved or very easy to solve. If you have accessible experiments and very little data, then you can go into an active learning loop, right? Something like what Melissa was talking about yesterday, so you can acquire data in a smart way. If your experiments are very expensive, but the community has assembled during decades a lot of data, then you can go into generative AI, as Patricia just spoke about a few minutes ago. And if you're between, then you can always do something like, you know, physics-informed or model-informed AI, as was discussed also before, for example, by Martin. But the problem is when you are, you know, in the poor situation on both sides, right? So expensive data to acquire and very few data points available. So when you're in that situation, then what you can do is either try to make the most out of the available data that you have. So that's what Alexander showed when we were in Kobe. I know that many of you were there about a month ago. But today I'm going to show you something else that is done in my group, which is trying to boost the experiments, right? So now we're not going to try to make the most out of the data, but we're going to try the simulations faster, which is the whole point of enhanced sampling, right? And this is work done in particular by Eline. The applications are by Lisa and Philip, and there's going to be some experimentation by Julia Giubertoni. So the whole idea, the whole problem with simulation time steps is that, well, it's not only that time stepping is expensive, it's also that we spend a lot of time in stable states, and interesting transitions are rare events, right? And then normally what we do is that we take the potential energy of the system, which is a function of R and P, and then we add on top of this an potential energy, the biasing potential, which is a function of collective variable set that describe the process. And it also has its own parameters B. For example, think about the size of your metadynamics Gaussians, thickness of your umbrellas. And then if we do this correctly, then we can happily overcome a free energy barrier and have a calculation. Now there's a lot of ideas, and it was shown also before yesterday, about using Bayesian optimization to explore the system space, right? So you can do alchemical changes, you can try to engineer a system to develop a certain behavior. What I'm proposing to you today is that you can also use Bayesian optimization to design the optimal bias for a particular system at the same time that you're designing the system itself, right? So we're going to use it to the simplest possible case, harmonic biases, as you have in umbrella sampling. You know that you can restrain your system to be in a particular stage of the transition, and you could do WAM, you could do M-bar, but you can also do something much simpler, that is using this information to estimate the gradient of different points of the transition, and then using some sort of numerical integration to get back a free energy profile. Now, of course, the question is, a priori, you don't know, because you don't know the shape of the free energy. Should I put my umbrellas like this, or should I put them like that? There's no way to know a priori, right? So the proposal here is to use Bayesian quadrature. And Bayesian quadrature, you can think of it as Bayesian optimization for integrals, right? So now, after Melissa's lecture, you're all experts in Bayesian optimization. So you know that the idea is to sample the most informative points to either explore or exploit, right? We have a surrogate model, and the surrogate model is going to estimate our free energy grids. But then we're going to have a very special acquisition function that is going to aim to reduce the uncertainty, not of the gradient, but of the integral of that. So the uncertainty of the free energy, right? So once we pick up a new point, we're going to update our surrogate model, and then we go into an act loop where we basically get new points, the most informative ones, and we refine our free energy. So let's see that in action. I have a short animation for you. In the first panel, you see the ground truth. Then you see the Bayesian quadrature prediction. Here you see the difference between the two, and here is going to be the error versus the number. So you can see how the method acquires new points. The points are basically tending to be somewhere around the inflection points or saddle points in the free energy, and that's because normally that's where you have the highest uncertainty. And you can see that very quickly you get to very low errors of around 1 kcal per mole. The question, of course, is how robust is this? So if you compare it versus naive sample grid, we see that we are pretty much always better than that. And what I also like a lot is that it's very hyperparameter robust. So if you try different kernels, different length scales for the kernel, then you typically always do better than naive sampling. So this is also something that is easy to use. Now let's try to put it to the test on more difficult problems than alanine and dipeptide. So first we go into polymer rigidities. If you zoom into your joints, in your cartilage there's a matrix of collagen, and this very important molecule is called hyaluronic acid, and it basically governs the mechanical properties, right? So it's responsible for you not getting arthritis before time. It's also very common to see it in cancer because it basically tries to mechanically lock tumor cells, and because of these nice mechanical properties, we also use it as a wound treatment material. And the reason why it has this nice mechanical properties is because it's ion responsive. So different ions bind to the side chains of this polymer, and then it can become more or less flexible. People didn't know exactly how this worked. A few years ago already, with the calculations on different ions, we were basically bending the polymer and getting a free energy estimation. Here you can see in blue the polymer in sodium, and in both shades of pink the polymer in calcium, and you can see it becomes 40% easier to bend it, so it becomes more flexible. And this very closely matches the experimental result of 47%. And basically what's happening is that the ion stabilizes and conformation of the polymer. But then, of course, what happens with other ions that are not calcium? What we did here is that we used two models because there's a lot of debate about divalent cations. Some of you are aware that they're very difficult to simulate because of, well, the singularity of the point charge in classical force fields. In a classical force field, of course, an ion is just a charge and it's just a charge and a couple of Lennard-Jones parameters, which means that if you explore the space of these parameters, you can actually explore the space of different ions in a way that is force field agnostic. So this is the surface that we get with Bayesian quadrature. Here you can see epsilon, you can see sigma. Here I have labeled a few ions that are known, and you did see that the lower part of the free energy is near where the calcium was. But now you get a lot of evaluations in a cheap way. Now let's go to another more scary case, like the nanoplastics effects on proteins. Of course, plastics are a bit pollutant in our planet, but also in our bodies. We decided to first look at the circulatory system because, well, it takes charge of the design of the plastics within your body, but it also, we consider that cardiovascular diseases are the top global cause of death. And here the idea is that if you zoom in arteries and veins, you see that the endothelium is basically a wall of cells that regulate molecular transport between blood and tissue, right? So in between of endothelial cells, you have a collection of proteins. And the most important of these regulatory proteins is known as VE cadherin, vascular endothelial cadherin, named after calcium-dependent adhesion. And, well, we discovered a couple of years ago that upon exposure to a certain types of nanoplastic, this protein breaks down. What happens to your body? You can see in this experimental, it's not so clear with the light, but basically in the control case, you see that the cells are happily moving, but they remain together. The membrane is intact. But in the polluted case, after only 6 hours, the cells are completely destroyed. They cannot stick together. And the simulation, what you can do is that, well, you can basically try to pull the protein apart, either in the presence of or plastics. So that's what you see here. The red case is, of course, the one without plastic, and you can see that the dissociation free energy becomes significantly lower, meaning that it's more likely to see a disruption event. If you bring a bigger plastic, this becomes even more dramatic, close to the case when you remove the calcium from the protein, so it loses its adhesive power. Now, again, the same question, how do you sample of multiple plastics? You use Bayesian quadrature. Here, the lines represent traditional calculations, and then each of these points was suggested by the method, and you can basically predict the risk that different size plastics pose to your circulatory system. And with this, I hope I showed you that the method is flexible, it's quite robust. We have also applied it to other things I don't have the time to show today, such as modeling and phase transitions. And finally, the form of the bias doesn't have to be harmonic. We are also exploring metadynamics-like biases. Thank you for your attention. Thanks to my team, and I will just leave you with a piece of advertisement from Amsterdam.
Questions?
Thank you. Very nice. Wondering, are these any methods available already? I saw you using Plume. Is the plan to integrate these among the modules of Plume? Or
Yeah.
Thank you.
We haven't published it yet, so Plume we use for the bias itself. For the smart part of the bias, so for the Bayesian quadrature, we're using some in-house code that we expect to publish at the end of the summer.
Thanks, Alberto. Very nice. The Bayesian optimization, do you use the gradients as well? Or do you use them during the integration that you use?
Yes.
Rather than just the values?
Yeah, this is a very interesting question that we have been thinking about. So what we do now is that we use the gradient of the free energy, the energy, but of course if you have access to basically the Hessian, right? So you have the derivative of the derivative, then this could be a lot better. In principle, this is expensive to get. However, there are a few LMPs that have cheap Hessians. So that's an interesting direction that we are considering for the future. We are not experts on those kind of machine learning potential. Someone is, we're very happy to chat.
Other questions?
How do you fix the integration constant when you integrate in the Bayesian? So you see that
there is this Bayesian optimization with the integrals. So I was wondering if you have an error, how this affects the constant, and if this affects the process.
Well, we normally only care about differences. So
okay.
But I don't know exactly what you mean.
Maybe we can discuss that later, because I don't understand either the specific setup. So, okay.
No problem.
Other questions? If not, let's thank Alberto again. Che veda qualcosa, ma cioè fate una presentazione dello schermo. Displays. Qua, displays. Poi fai mirror. Apply. Scusa, forse anche controllo L. Okay, perfect. We have Giovanni Trezza from actually the University of Grenoble-Alpes, but the work was done at the Politecnico di Torino. And the title of his presentation is going to be Quantifying and Mitigating Data Bias in AI from Model Robustness to Energy GNOME. Here you are.
Thank you for the presentation, for the introduction. So, in this presentation, I'm going to talk here about cross-domain data bias. So first, observation what it is and why it matters. Then supervised approach that we propose via classification for detecting and trying to circumvent it. Then a couple of validation process for showing that effectively it is supposed to work. And then we try to apply it for screening the GNOME database, which is a database comprising 400,000 AI-generated structures from Google DeepMind publication of a couple of years ago. And then, so what is, imagine that you want to train a model over a specialized database for predicting a property of interest, and that model will use all the information that you will feed in. In particular, that information can be divided, say, in a signal and in a bias, which is necessary actually to predict the target, and the bias which is not, as far as the physical property you want to predict is concerned. But of course, the model does not know how to discriminate between these two information, or will take everything. Actually, if you train a model and then you want to apply this model for predicting the properties over materials, over samples in general that share the same joint distribution of signal, bias, and target, everything works. The typical in distribution case, this is the typical case where where the out-of-the-box samples are actually samples randomly from the same database, where you got a training set, and so actually it is really when you have training, validation, and testing set, and testing set split for the same data source. Completely different is the case where you try to apply a model trained over a source of data, and to samples coming from a completely different source of data with a completely different genesis, and here it is the typical cross-domain data bias. So say that we are actually in the situation where you have a model, a regression model trained over a training material space, and which is actually, say, a small subset of the whole material space, and you want to apply this model for predicting the property of interest for that model over materials with, in principle, a different genesis. The first thing you would like to check is if this material actually to the training material space, and so if you are effectively allowed to use that regression model. And so what we tried to apply actually a set of binary classifiers that taking into account both the training material space and materials coming from the material space, but everything fully supervised. So validation protocols, first for showing that effectively it works. The first question is that if this classifier and regression performances are correlated, so say that we here everything simple, so all the database in this validation protocols are tabular data, so no graph neural networks, but simply a array of handcrafted descriptors. Say that we have a database of this kind. We apply, for instance, MathMiner, which is a tool for extracting handcrafted descriptors, and then we train a model. We apply SHAP for ranking the important features, and in the end, we are in the situation with the list of materials to target for those features. Actually, then we apply an agglomerative clustering over those features for splitting the database into two clusters. Actually allows to have a meaningful split of the database, so not just a random split. And the idea is then to train and test a classifier for discriminating between these two clusters. And then train and test a regressor for predicting the property of interest only on one of the two clusters. And then to compare these two performances, the classification performances over the testing set. But for doing everything in a controllable way, we progressively inject noise in the clustering of the two clusters. And so we will check that classification performances, of course, will decrease as the noise will be injected. We will see what happens with the regression performances, since the regression will be allowed to predict only materials labeled as cluster A. Of course, so those labeled in a, say, pretended to be as belonging to cluster A, but actually be cluster B because of the noise we have injected. And this is the result. Here is an example, say on the SuperCon database. So is a collector of nearly 13,000 materials experimentally tested for superconductivity, only composition. And here on the verses, you see the regression performances, while on the horizontal axis, you see the classification performances. This is the area under curve. And so you see that increasing the classification performances, actually all the regression metrics improve in terms of coefficient of determination, mean absolute error, and root mean squared error. A second validation protocol is about the source of the, say, general database. Actually, what I've done up to now is to consider only one database, which was the specialized database, dividing it into two clusters. But of course, this would not happen in a real scenario. In a real scenario, you would have a specialized database and a proxy of general database, post database. So what I do here is to have actually the same procedure in terms of clustering of the specialized database. Actually here I will use only half of cluster A, both for the classification and in particular in this case I will take as class 0 material 10 random subsets from materials project, and this allows to construct 10 classification class models for discriminating between cluster A and out of cluster A materials. And then a regression model that is trained all the same cluster A used for classification. And what I do is then to take all the other materials, both the other half of cluster A and pass them through the classification filter. Those materials, of course, have never been exposed to the other training, and in particular, the idea is that that only the materials actually passing the filtration from the classifiers are enabled to be predicted by the regression model. And this is actually the result in this case. So on the vertical axis, you see always the regression metrics. On the horizontal axis, that's the stringency threshold, which is considered to be kind of the severity of this classifier-based filter. And think about the average probability of the 10 classifiers for a material to be predicted in the same training material space. So armed with such methodology, then we try to apply it on the GNOME database for screening those nearly 400,000 AI generated. And this is an example with superconductors, and always here composition based because supercon database is solutions. And here we isolate kind of 139 candidates having with TC predicted over 40 Kelvin and greater than 0.5 in terms of the classifiers. Here in particular, 3 samples. One is potassium hydride, which resembles kind of the lanthanum hydride. There are hydrates under high pressure, and the other 2 are cuprates. And as you know, many non-conventional superconductors are copper-based. But then we went further with thermoelectrics. From here, STM database, which is always a composition-based database of experimental data for thermoelectric materials. Then we tried with perovskites, and here also the structure was available. So for the regression model, we used the equivariant graph neural network, and the same thing for battery cathodes. Options are actually in this web app, Energy GNOME, where you can go and say it is an interactive site like Style Materials Project, where there are all the predictions of those materials and the insights of the reliability. And so, as a conclusion, we developed this methodology based on classification. This was published in JSIM, and it got also the front cover of the issue of February, and then employed this methodology for finding potential energy materials over the GNOME database. Thank you.
Are there any questions?
Very interesting work. Do you envisage an application also to understand, for example, whether learning interatomic potential can be trustworthy or not for certain specific materials? So we see these foundation models. Will you be able to predict whether we can, let's say, out of the box for a new material or not with this method?
Okay. You're talking about really extrapolating directly. Actually, this only chops things for what the regression model would may not reliable. So it is not really for extrapolate. Actually, there are some works for extrapolation. There was one of the last works in the group of Raffaele Gomez-Bombarelli, who at MIT, and in that work they, in a tabular dataset, actually recasted the features in such a way that the model showed them an out-of-the-box sample as included in the training data, in the training materials, the training space of the samples. So, but to my knowledge, there is not a pure extrapolative machine learning.
Any other questions? If not, let the speaker again, and we are now ready for the coffee break. As Ivor said, we split the session a bit differently than in the program. So please, 8 minutes break. Yeah. Okay.
Okay, let's start with the last session for today. So before we start, I just wanted to show you where is the conference dinner. So you should enter through, I think it's, visibility is great, but you should enter through this door, if you see it. And it's basically the conference dinner is going to be here in the yard of this university building here. I sent that location Slack, but so it's the restaurant is also belonging to university. It's called Barbakan. You will see, but I just want to show you where you enter. So this should be open from 6. So you come at around 6. I think that's all the information I had to. So now you can go back to your presentation. I'm also glad to invite Patricia Ramos to show what she did. So.
Hi everyone. My name is Patricia Ramos. I come from Portugal, and I'm going to present to you work that is being done with my colleague José Oliveira. Actually, this work is about multimodal modeling, which was a subject that Kevin brought to the panel 2 days ago, and it's quite interesting because this is all subject of working group 3, which is one of the working groups that belongs to DIMON, and that's his challenge for us also to try to tackle this subject, and this presentation will be about that. All right, so So what is multimodal modeling, especially for material science? You already know that material science is a subject where you have data, in this case of crystals, which has lots of information in different modalities. And the idea in multimodal learning is to integrate these types of data in a single model. So, of course, this depends on the situation at your modality to be tailored for a particular architecture, which of course is dependent on the data. So we are talking about integrating the usual information, which is chemical composition, the crystal structure, the description of the material, in a single model. And you have here on the right one of the most famous works until now, which was published in 2025. And you have here the 4 modalities being integrated: crystal structure, the text, the description of the material, and the density of states and the charge density, being all put on a latent space where the information is fused, and the properties about the materials are predicted. So the idea is to use this unit model that integrates this type of information to predict complex properties like electronic, thermodynamic, and so on. Of course, the idea is that when you collect this information, you will be able to complement the information that you have about the material. There are, of course, the idea that the accuracy will improve. Okay, what are the key challenges associated with that? First of all, the data alignment. This information comes from different types of data. We are talking about text, which is of course words, but you have also images, and you have, in terms of crystal structure, you can have the graph data. And this must be aligned when you put this into a unit model. One famous model that does that is CLIP. I think everyone has heard of it, which is a model that integrates text and visual information, and the text is a description about that. And it has a procedure that it's called contrastive learning, which fuses the information in a latent space, which tries to approximate the entities that belong to the same material. The problem with this approach is that you only are able to align two models. So it was important to have a scalable multi-model framework that would be able to integrate not only two but more than modalities. So that's the first issue. Okay, of course, if we think about integrating more than two modalities, you will have to have an advanced model that can fuse this information and using advanced techniques. So feature integration should be advanced if you are thinking about more than two modalities. And of course, computational demands, because we are talking about information that comes from different types of data, images, so on. So that's also one issue. And of course, when we talk about data sets and databases, usually the information is not available in all these modalities. So you have to prepare your data set with this type of information to train your model. And it would be great if you could, at the end, interpret and see what are the modalities that are more aligned with the properties associated with. So this architecture of the multimodal model. So we used Alexandria to train the model, and you have on the left the three modalities that were used. So you have the chemical composition that was encoded as text. You have a 2D crystal structure image, which was encoded as image. And also, this was an enhancement that we made from the last presentation, we also tried to include an X-ray diffraction image. And the idea here is also, one of the novelties would be not also to be able to integrate images, which is the first time that is being actually done, but also to use foundation models. Everyone has heard of it during this week. And I really believe that they are not the future, but the present, because everyone knows that it costs a lot to train a model from scratch. And if you are able to use a model that is already pre-trained with a robust train situation, it is much interesting and much important and much easier to get your results if you can actually use that first start and fine-tune on a specific domain data set. So these three models that we used to encode the information are foundation models that were gathered from a repository that everyone knows, which is Hugging Face. So, and these three models were then fine-tuned, and the output of the models were used in a few models that fused the information and was trained to predict the materials properties, which actually were directly available in the Alexandria dataset. So that is the idea. All right, so first of all, remember that we have our composition, chemical composition. So how can we represent a composition? And we did it as a standardized text to be able to be the input for a transformer-based model. This is actually inspired by CRANET strategy that also encodes chemical compositions as text with elements and atoms separated by spaces. So that's, and this is actually this is a good strategy because this actually is this tokenization is compatible with the Hugging Face model that's used. in the multimodal model. The second problem was how could we generate the 2D crystal structure visualization. And actually this was done with the same approach that you know from Materials Project web interface. So we use Crystal Toolkit integrated with PyMatchN to create the 3D structures, and then we use the Dash framework that actually renders the 3D models and automatically that are automatically screenshot to be able to be saved in a 2D PNG file. All right, what about X-ray diffractions? Well, also inspired by Materials Project specification, we load a C file for each material, and actually convert this to a standard structure that was used to calculate the XRD patterns. And after having these values, we interpolate the intensities using Gaussian broadening with a sigma 0.6 and normalize the intensities to 100 to be for the plots to be compared to each other, and then of course save the file in a PNG format. Okay, so now let's talk about the encoders. We have already our input prepared, so the data set is already prepared. Now we're talking about the models that are going to encode each modality. And we have two different ones. The first ones are from the text, from the chemical composition. So we are talking about model that is, it was pre-trained from Google. This is a huge model which has about 108 million parameters. I should say that this model was downloaded 16 million times last month, so it's quite a huge number, I think. So that's why I say that these models are really important now. So the input was the sequence of chemical elements and the coefficients of the species. Then we fine-tuned the model, okay, using the Alexandria subset of materials. And what about the architecture of the model? Actually, the architecture is quite simple. It's a transfer encoder, okay, with 12 layers, and in each layer you have 12 multi-head self-attention, okay, modules with fully networks and layer normalization. And the output is a 768 dimensional embedding that is going to be used by the Fusion model. So this is the text. Now let's talk about the images. The images used a different model from TIM, which is a library that has image models employed in PyTorch. Actually, this is also available in Hugging Face. It has 90 million parameters. The input I already explained. It was also fine-tuned using the Alexandria dataset, and we used one model for each modality. Okay, the architecture is a little bit different than the previous one. It's an hierarchical transformer when you have metaformal blocks. Each metaformal block is composed of convolutional neural networks and mixed with attention mechanisms. So that's that. Okay, and the output is also 768 embedding, which is the output of the encoder on the final layer, and will be used as input for the Fusion model. Okay, what about the Fusion model? In the architecture that we employed, actually we can use unimodal or multimodal modalities. So if you are using unimodal one modality, you use the unimodal approach, and then the encoder, the output of the encoder will have one head which will directly predict the property using a task as a regression. Okay, if you are using the model with two or more modalities, then the encoders need to fuse the embeddings, and you have the Fusion model that gets the output of the encoders, and that's the Fusion model that has the final layer, which predicts the property, in our case at the moment using an MLP. Okay, so you are already seeing all the pictures. So train the full model using the 3 modalities and the encoders and the fusion. So everything was integrated. So we used the data split of 1,000 materials just to prove the concept, 80% to train and 10% to validate and test. So, and imagine that when we were training the multimodal model, we were simultaneously encoding, made the tuning of the encoders and also training the fusion model. And the parameters were more or less the ones that you are used to. Of course, we can do hyperparameter optimization if you want in this. Okay, let's talk about the results. I have to say that the results are still preliminary because the data set is quite small yet. So we need now to upscale this to use all the data set of Alexandria. That's the next step. But the results are quite good. We have on the first 3 lines, you have the results from the 1 modality. So you have the composition as being used as 1 modality, or the structure in a visualization, or the XR diffusion. Okay, then you see that in the first case, you see that the composition was quite helpful to predict the total energy and the magnetic moment. And the structure was quite competitive to predict the formation energy, the energy above the convex hull, the volume, and the density of states. And actually, the X-ray diffraction was only important for the gap. We cannot actually be connected to results, because I must say that you have to extrapolate a little bit the data set to get the results more robust. But one thing is important is that when you use the 3 modalities, results improve in all the properties, and the gains are between 6% and 30%, even if you compare your 3 modalities with the best case of 1 modality. So the results are good for us to pursue with IDEA, and that's what we are intend to do. But of course, the conclusions are promising. So we could integrate the chemical composition and the visualizations of structure and the X-ray diffraction in a scale architecture, which is quite flexible in the meaning that you can add more modalities if you want to. We improve we prove that we can improve accuracy, which of course is the main issue, and we believe that there are some synergetic insights to be collected from this. When we combine this information and see what kind of it's good to interpret what kind of a model are important for each property. So, but the practical impact is of course there. We can actually predict the properties of the materials with this kind of approach using several modalities. But we are not yet done. Of course, it's in your mind that we should encode the structure also, and that's for sure. It's the most promising modality of all. The problem is that we don't, as far as I know, we don't have pre-trained foundation model for the structure. We already have foundation models, but they are not so easily available as in Hugging Face. And I think that's the next step for the materials community, to dispose their models in the repositories that are very well known, and of course the number of downloads will increase for sure. Okay. We also would like to compare this framework with a framework that integrates state-of-the-art specific models for materials, okay? And in terms of research efficiency, we already know the result. They will be much less difficult to train, much resources intensive, and let's hope that will not be the too much for them to be used. But I think, in my perspective, the predictive accuracy, for us to get the same predictive accuracy, we will need to have ARC-train and probably the use of this framework with foundation models will be the situation for the near future. Okay, and we also would like to use a fusion model that will be more advanced. We are using an MLP now, but the transformer will be much more efficient, of course, but it needs more time to train. And we didn't have enough time to test this all, but we are sure that if we use the foundation model that is more advanced, the results could also improve. And that's it.
Thank you. Is there any question?
Hi, thank you for a nice talk. So my question is, did you start with such a big model like Electra? Why didn't you start with I don't know, some versions with 4 layers and with the embedding vectors with less size? I think it would do the same, and you could compare the results much faster and see whether your model is all parametered.
It's quite easy at the moment to fine-tune a model from this kind of repositories. That's why I think the availability is it was the answer to your question. It's much easier to get these type of models, and I think that we will try to use other specific models. From a start, it was more easier to use these models that are available, are very easily to fine-tune, and the results are usually very promising. The problem is that they are very general, but the idea is that if you fine-tune them in a sufficiently big data set, probably the results will be the same. And in terms of image, as far as I know, we don't have a trained model trained with images for materials, so we didn't have any chance of not using this. So that's the main reason.
Any other question?
Thank you, Patricia. I have a question. Can you give us more details about the fusion of all this information? Because so I'm aware that, like in contrastive learning, you have the contrastive loss, try to align the different representation into the same embedding space, and I didn't fully follow what happens here.
The fusion model is not very sophisticated. You just collect the embeddings from the modalities and you concatenate them in a very simple way, and then you put them at the moment in an MLP that actually exploits a little bit the number of neurons, and then gets out the prediction. And of course, you can have you can have several layers, not only one. Actually, ours is only one hidden layer, but you can of course increase more. You can use a fusion model that is more advanced, like using a transformer. That's the two main possibilities right now. Of course, the contrastive learning approach is more reliable in the sense that you are able to, in the first place, put in the latent space the information, approximate them using an optimization, and then improve the accuracy based on that. But this is restricted to 2 modalities. So if you have more than 2, what shall you do? So I think the idea now is to have some if you want to use more, you need to have a different approach, and And why not? I spend so much time with two modalities to have more. So let's try, even though less sophisticated fusion model, but a one that is scalable and you can increase your modalities. And I think if you have a fusion model that is sufficiently sophisticated, you will get good results too, comparable.
Thank you.
Thank you. And is there any other question? If not, let's thank Patrizia again. And okay, great. So Mandira, please go.
Hello. Good afternoon, everyone. I'm Mandira, currently a postdoc researcher at University of Turku in Finland. And today I'll be presenting our work on understanding surface chemistry of aerosols by computing X-ray spectra using DFT and machine learning. So let's have a quick introduction on aerosols. So aerosols are liquid or solid particles suspended in our atmosphere. Their size vary in micrometer ranges. They originate from both natural sources like sea spray, mineral dust, and man-made sources like industry and many other things. So despite of their small sizes, they have huge impact. They influence cloud formation, sunlight radiation and absorption, air quality, climate, and even human health. Studying aerosols is very important in order to understand the broader atmospheric processes. So in this study, we are focusing on NaCl aerosol, sodium chloride aerosol, major component of sea salt aerosol. They mediate to the through their surface to the atmospheric compounds, mainly to the water, which is most abundant. Now, this interaction influence their phase, reactivity, even their transport, and obviously their chemical environment. And there are some experimental evidence from our collaborator group. So they observed experience a shift of 1.1 EV in the sodium 1s XPS peak when sodium chloride, when the NaCl aerosols reacts with the water at low humidity. So while this study gives us the base of our while this finding gives us the base of our study, our broader aim is to decode the surface chemistry of aerosols. And to do that, we have three objectives. First, modeling the sodium chloride aerosol surface, then exploring the water adsorption on the surface, and next is computing the core level binding energy shift in sodium 1s. So to achieve our objective, we have three computational steps. That's with modeling the sodium aerosol surface, which is sodium chloride 001 surface using density functional theory. Then computing the water adsorption structure search over this surface using Bayesian optimization and density functional theory. And next is core electron binding energy, that is sodium binding energy calculation, again using DFT. So for the DFT part, we are using FHIM's code, and this is the level of theory we are using. And for Bayesian optimization part, we are using Bayesian optimization structure search code, and you had a detailed talk on this yesterday by Professor Todorov. Now, first I will talk about the NaCl surface and water adsorption over the surface. So this is our optimized sodium chloride surface. We prepared this surface from the bulk sodium chloride, and this is our optimized surface, so which is 6-layer thick. The lattice parameter is 5.625 angstrom. The top layer is round. That means the sodium and chlorine atoms of the top atomic layer are displaced along different directions, are displaced along opposite direction along Z. and this is the rumpling amount. And this finding is in well agreement with the existing literature. Next is the water adsorption structure search. So for this part, we use Bayesian optimization structure search code along with density functional theory. So already know what is the core idea. So the core idea is to find, is to optimize this adsorption energy as a function of 6 degrees of freedom of water adsorption. So this is the sodium chloride surface and this is water molecule. So 6 degrees of freedom of water adsorption by means 3 orientation, that is alpha, beta, gamma, that is rotation of the water molecule around the principal axis. And then the 3 translational, that is translation of the water around the 3 principal axis. So when this water molecule will change its orientation, the z axis, when the distance will vary, obviously this adsorption energy will change, and we want to optimize with BOSS and DFT this adsorption energy. So now this is a 60 BOSS. Okay, so the next to decide on the search space of the 6 variable. So for alpha, beta and gamma, the search space is 0 to 360 degree, which is periodic. And for XY, that is over this surface, which is also periodic, which is this marked red box, marked in red color. And for Z, this is non-periodic. This Z varies from 2.3 to 5 angstrom over this surface. Okay. So next, this is the workflow. So that starts with the building block, which is sodium chloride surface in the single water molecule. Next step is to compute the adsorption energy, and the 6 variables and this adsorption energy will be the data for the machine learning modeling for BOSS structure search, and then it will feed the data. Next is evaluating the next evaluation point, then again compute here, and those data is again added to my previous data, and again this loop will go on and on until we reach to the convergence of our global minima. So as you can see here, we use acquisition function ELCB, which has the property of exploring and exploiting the data. And for kernel, we use STDP for the periodic, that is for the angles and the XY space, and non-periodic kernel for the Z. So we started this initially 30 data points, and we reach the global minima has been reached after 2,600 iterations. Okay, so at end of this after end of this step, we have adsorption energy as a function of 6 variables. Out of I am showing the adsorption energy in the XY plane. So as I mentioned earlier, this was our search space in the XY plane. So this is how the adsorption energy looks in the if I'm cutting it through the XY plane, it looks like this. So as you can see, these are the minimum energy positions, so which are above this sodium atom, not exactly over the sodium atom, rather displaced from the sodium atom. So this is from the BOSS search. So after having the predicted global minima structure from BOSS, we again relaxed it with density functional theory, and this is the relaxed structure, finally water adsorb structure over the NaCl surface. So till now we have the optimized sodium chloride surface and all the relaxed water geometry over the sodium chloride surface. And next step is to computing the sodium 1s binding energy shift for sodium chloride 001 in periodic conditions. So to do that, we are using delta self-consistent field method. Now, while computing the binding energy for periodic solid, it is important to compute it with respect to energy of the highest occupied state, and that can be obtained from the difference of 2 delta result. So say it is delta SCF1 and delta SCF2. So the first delta SCF involves the delta SCF calculation the core electron. That means if I remove one electron from the core level, so which is this one, so this energy corresponding to this system, and energy of the ground state. So from this is first delta SCF calculation, and the second delta SCF calculation is the first ionization energy. That is, I am just one electron from the highest occupied state. So that is second delta SCF calculation. So from here, as you can see, the energy of the ground state cancel out. So finally, you need this to energy value to compute this binding energy. Now, while doing this, we are adding a nuclear charge of 0.1 E on the target sodium atom just to attract the core hole to that atom. And to neutralize that nuclear charge, we are a background charge to the system. And while we are doing this, to neutralize the interaction between periodic images of this background charge, it is important to check the binding energy convergence of the system with changing the supercell size. So after computing this binding energy, we actually computed it for 1x1 cell, 2x2 cell, 3x3 cell, 4x4 cell, until we reach the convergence to the match. And this is our final result. So this is for the clean surface. So as you can see that this is energy for layer 1 and layer 2, 3, 4. As you can, so this is our surface side view. So this layer 1, 2, 3, 4. As you can see, binding energy of layer 2, 3, and 4 aligned with each other and very much different from the layer 1. And why it is so? Because the environment. Because the chemical element of layer 1 very much different from layer 2, 3, and 4. For layer 2, 3, and 4, they are seeing the same kind of environment above and below. But for layer 1, it is that. So when water gets adsorbed over the surface, as you can see, the water gets adsorbed over this sodium site. Let's say this is site A and this is site B. Here we showed the result of site A and site B. What is the absorption and binding energy of this sodium and this. So after water gets adsorbed, now we are getting different sodium binding energy signal from the site A and site B. That means symmetry is now broken. And then as a whole, the binding energy, the sodium 1's binding energy shifts to the lower value, and difference between this layer 1 and layer 2, 3, 4 now has been decreased. So we have computed binding energy shift from this site A and site B, which is 0.64 EV. And the experimental shift is 1.1 EV at low humidity. Obviously, there is a mismatch in the result because here we just considered binding energy of layer 1 and only binding energy of layer 1 and binding energy of site A and site B. We need to consider binding energy of other sodium atoms over for the system, and also we considered only one water molecule, which is obviously not a low humidity. We need to consider more water molecule to compute this binding energy. So that is what we are doing currently. So finally, this is my conclusion, that well-guided structure search, that is with BOSS, we could manage to explore the whole adsorption energy landscape, and the global minima structure is consistent with the literature. We applied the SCF method for a surface calculation in periodic boundary condition, and the computed binding energy shift concludes that okay, there is surface chemistry changes for this NaCl after water interactions, and now ongoing work includes the increasing of water coverage to capture more realistic aerosol surface behavior, and obviously we are developing a machine learning model that can predict the XPS spectra from the structure. And finally, I want to urge our group, Materials Informatics Laboratory, the Research Funding Energy, and the CAC Computing Facility of Finland. Thank you.
Thank you. So, any questions? I don't see any. Okay, so there are no questions. Thank you.
Okay, hi everyone. Visibility isn't great, to be honest, but I will try to maybe explain what we do. So this will be more like a business presentation than the scientific presentation that you all heard. But so my name is Stipe Lukin. I'm one of the co-founders of Kalpatech, and we are, let's say, a deep tech startup, innovation-driven deep tech startup, which deep tech essentially means that we are focused on developing technology, and innovation-driven is that we kind of developed it based on certain innovations. Now, we're founded in 2023, but started working on this in late 2021. And just to give you like a context of what we do, essentially we are focused on doing comprehensive solid form landscape exploration, which is effectively experimental screening, and full structural characterization of any new solid forms. Now, that isn't that, say, crazy, but the fact that we want to do this with very extremely small quantities of material is what is, let's say, new here. And of course, we want to perform this in ordinary laboratory. As any startup, we also have some kind of revolutionary vision, and our vision is to revolutionize the material analysis. But I'm not gonna dwell into this. So a little bit more context. So right now, or for the last couple of years, there was like a really huge streak into going towards the autonomous laboratories, especially when it comes to the materials discovery. Now, this is just, let's say, a continuation that you have on automation. So once you are able to automate something, let's say preparation of materials and data collecting, then when you add the analytics, you're able to perform decision making, and then you are able to go on autonomous level. Some of these papers, for example, the cedar from the Nature, it was a big deal when it came out, but then essentially it had one flaw. The analytics that they performed in this paper was kind of slow, especially when it comes to the powder X-ray diffraction. So they generate quite large number of materials, and then they claim some of those materials were novel. They used powder X-ray diffraction as an analytic technique. Later it was found out that just some materials that were already known, they kind of misidentified them as new materials. Now, with generative AI, what we have today is more and more research on, let's say, dreaming up materials and molecules that have desired properties. Then hopefully some of those materials can be prepared, they're stable. With automation, some synthesis of them can be also, let's say, accelerated. So to a certain degree, you know, if whatever you dream up or in the end, you have to prepare it and validate it experimentally. And it appears that this experimental validation is now starting to become a bottleneck in certain applications. So this is something that we are actually tackling. Now, in materials discovery, essentially there are kind of maybe two approaches, generally two approaches. So you can either generate, for example, crystal structure prediction can be an example. This you can just generate a lot of crystal structures that may or may not exist. And then you can perform some kind of solid state calculation on them, calculate some properties, etc. Or what I believe that people that do solid state calculation prefer is to get the experimental crystal structure and then actually go from there. You can maybe do some perturbation there, explore and fine-tune that material. Now, if you go, first approach or the second approach, you will converge in the fact that you will need crystal structure of that material. So this is the graph of let's say the number of molecules in the CSD database. Now the CSD database is relevant for us because we are focused on small organic molecules. So not that much on inorganic, but small organic molecules. This is duly from business reason because the pharmaceuticals are the market for us. In the last, let's say, couple of years, around 55,000 new crystal structures were deposited every year was deposited in the CSD. Now we also have crystallography open database, which is free. It has over 500,000 structures. CSD has, I think, over 1.3 million, but it's not free. When you look at the, let's say, methodology of how to obtain the crystal structure, now I'm just saying this from the experimental point of view, over 97 to 98% of these structures were developed by using single crystal X-ray diffraction. So if you can grow the single crystal, the structure today, it's almost automatically, even some of the machines that you buy literally solves the structure during the data collection. But growing single crystals, it's not very easy, especially if you have any kind of demanding material. So the powder X-ray diffraction is something that around maybe 1 to 2% of deposit structures are sold from powder data. Now here, the sample preparation, super easy. Data collection, super easy. Analysis, not that easy, apparently. And we also have electron diffraction, but this is something that is kind of emerging, and the number of structures sold by electron diffraction are still negligible on, let's say, on this scale. Now we are in this powder X-ray diffraction, let's say, kind of world, and we are focused on powder X-ray diffraction, specifically because you can analyze data very quickly and you can prepare it very easy. Now, let's say one of the applications that we are building and have in automated end-to-end crystal structure solution without expert input. Okay, so here end-to-end solution means that you collect the data on the machine, diffractometer, you put that data into the pipeline, to the model, give it maybe some metadata, non-experts data, let's say, and you get the result. Expert in this sense means that you do not need, for example, crystallographer that has, experience with powder X-ray diffraction data, or just crystallographer at all. So what we did essentially is we built we call it AI physics engine. Essentially it's a software, so it's a generator optimizer from, let's say, from scratch. The reason why we did this, which seems insane, is that the, let's say, current things that we could use are either, you cannot use it commercially, and they were too slow for what we need. So usually you cannot maybe use it on graphics cards, etc. So based on this, we built what we call a crystallography digital twin that we use for creating the data set and training the data. And when we started first, we went with synthetic data. And when you evaluate the model and you see the output, everything looks great. You know, kind of what usual pathway that you go in academy. But when we put the real data, so let's say real experimental data, these models did not perform so well. We spent more time in the last 2.5 years to make those models work on real world data than just building the models, etc. And the, let's say, inclusion of domain knowledge was maybe the main factor that contributed to this. So just an example of what I mean by this automated end-to-end solution. So this is the routine, the diffractogram that was collected for 5 minutes. Essentially, if you are going to solve crystal structure from the powder diffraction, you will collect data for 50 minutes, 1 hour, several hours, especially if it's maybe inorganic materials. And this is 2 to 72 theta range. So essentially, we solve the structure from powder using direct methods. This is the molecular structure. We can extract the unit cell parameters, and when you use the direct methods, if you fail to get the cell parameters right, then you'll fail in determining the structure almost always. So the idea here is that what we do, how we validated this, is that we collected the sample on laboratory instruments, and then the same sample we sent the synchrotron, and then we get probably the best powder X-ray diffraction data that you can get. And then we can compare, for example, how well we can extract or get the crystal structure out from the laboratory versus the, let's say, synchrotron data. Essentially, this graph on the x-axis, you have the total counting time, or let's say the collection time. So when you have a sample, the longer that you collect the data, you can have much, much better quality of the data, and then you can increase the probability of solving the structure. Now, usually when you want to solve or obtain crystal structure from the powder diffraction, you use simulated annealing, which means that you build the structural model, and then you just, perform random search, hoping that you will get some local minima, and that will be your crystal structure. Now, when you start with that, from the beginning, you have certain assumptions about the sample. Now, let's say the biggest improvement that we have here is that when you look at the really, really short measurement times, like 5 minutes and even less than minutes, we can obtain the unit cell parameters in very, very high percentage. And the similar trend is with this crystal structure solution as well. Now, what this essentially is going towards is that you can get kind of let's say your expert crystallography assistant. It's probably targeting the non-experts. You have a lot of, let's say, synthetic chemists that can prepare material, and that they can collect the data, but without, a crystallographer, they cannot do anything with that. So this is kind of aimed for them, but also it's tailor-made and aimed for the industry application that you have in pharmaceutical industry, but also in, for example, cement industry, where crystal structure determination is not that important, but the quantitative analytics is. And the goal is to have data collection and structure determination in less than 15 minutes. This is all part of, let's say, our materials discovery platform, where just obtaining solution is is one part of that. The second part is actually doing screenings. Now today, especially comes to the pharma industry, in the beginning you have very small quantities of sample. So if you want to do polymorph screening, salt screening, co-crystal screening, and then you usually optimize for solubility, you need grams of materials to do this. For this reason, there is no justification once you obtain several of your lead candidates to scale to grams the synthesis preparation of that, because you have this in milligrams. So what we can do with this is we can take much smaller quantities of sample, and we can obtain the information on huge number of experimental conditions. So we are able to do over 1,500 high throughput experiments per day on ordinary laboratory instrument, which none of the manufacturer of that instrument is going to tell you that it's possible, because they can do it. So you cannot see us, unfortunately. So these are my co-founders. We are a very interdisciplinary team. So a chemist, physicist, mathematician. We work, let's say, we work together for quite some time, and we know each other way before even we started with the company. We also have some advisors. Here's one person that you might recognize. And since we went, let's say our background is from 4 different scientific institutions, we also are partners with, let's say, many scientific institutions here in Croatia. Okay, thank you very much. If you have any questions or anything, we can discuss or talk now or later.
So, any questions?
Thanks, very cool to see this being done in industry. I didn't get it, so what's the nature of the method that you use to resolve this, to get the structure out? It's a generative model, it's a...
Sorry, can you...
Sorry, so how is it that you generate the structure from the composition and the spectrum? You have some kind of generative diffusion-based model, you have, what is it?
Okay, so essentially what we do is we input the raw diffractogram. So our training data is that we create the data set of diffractograms. Essentially, that's why we built the entire thing, to be able to simulate the real world diffractogram. So it's not just, okay, you can take a CIF file, and based on the position, you can put some, let's say, some peaks, peak size. But the thing is, this synthetic data set is going to work only on synthetic data. So once, if you want to do it or apply it to real world data, you need to have either a very, very large experimental data set, which you cannot get. It doesn't exist. I'm not aware of its existence. You know, you have some data sets that have like maybe a couple of thousands of experimental PXRD diffractograms. But essentially, to train our model, we needed like millions of them. So the only way was to really simulate that. So we also incorporate ray tracing, in essence, to really get the synthetic data to be as most close to the experimental data it could be.
But did I understand correctly? You're able to go from a diffractogram that you get from experiment, for example, to a structure.
Yeah.
So how does that work?
So okay. So what we did is we build a model into which you put diffractogram. It extracts peaks position, extracts the intensities, and then you can solve the by using direct methods. This is essentially how you solve in single crystal data. So you get the intensities, and you can get the structure like the usual way that
like a refilled refinement or something like that.
It has in essence you can use it for refilled refinement as well.
Okay, but there's not a generative component to it.
No, there is no generative component.
I see. Okay, I'm with you. Thanks a lot.
Any other question?
Hi. Nice talk. So one of the advantages of getting the expert out of the loop is, of course, that perhaps you could do faster predictions. In the sense that you don't have to send it to the lab, have someone analyze, etc. For any of your clients, is time actually an issue? So to the point that they would to have, a prediction within a minute, ideally maybe on a portable device, something like that, which of course is very difficult for this kind of thing. But
sorry, I don't hear you very well, so I'm trying to kind of fill the gaps with what exactly your question is.
Yeah.
Sorry.
Yeah, I'm asking if it's important. If it is important.
Ah, okay. Yeah. So for them, for example, for high throughput experiments, throughput is to achieve that what it takes 5 days, because the preparation is faster, data collection is faster, and data analytics is much faster.
I'm not sure if you mentioned that already, but can you also do somewhat disordered structures?
Sorry, which structures?
Structures that have some disorder in them.
Ah, disorder. Okay, no. So essentially, this would be like any crystal structure that you want to solve, whether it's from the single crystal or the powder. You get like ideal structure. If you have some intrinsic order, yeah, you can see it depending on the solution, right? So for this kind of things, if you're an expert and you get the solution where you have disorder of the atoms, you will recognize that immediately, right? So you can get that, but we didn't actually went that far to, let's say, incorporate that in automatic fashion that you can get the result of that.
Okay, so it's not there yet, this technology.
So it's not?
Do you understand that correctly? You don't? Okay.
Sorry, I didn't.
Any other question? If not, let's thank all the speakers again and see you at the dinner.